Welcome everyone to our final day of EY's Global Blockchain Summit 2021. Today's masterclasses will include topics on technology, privacy, and scalability. Here is your host with the most t-shirts, that is Paul Brody.
All right. Good morning, good afternoon, good evening, everybody. I'm Paul Brody. I am your host, your guide, and I am still apparently the EY Global Blockchain Leader. So far, so good. Haven't done anything wrong yet this morning. This is day 4 of our Global Blockchain Summit. It is our last day, and we are wrapping up today with a focus on privacy and scalability with a series of master classes. We have more excellent content for you today. I'm going to run through what we've got before handing it over to our first speaker. The first speaker of the day we're going to have right after this introduction explanation is Barry Whitehat. Now, how much does Barry value his privacy? Well, there's going to be no streaming video of Barry, and there's not even going to be a picture of him. But he is going to talk to us about what the limits are for privacy, right? We want the maximum level of privacy possible in the work that we do. And we think it's really, really important for consumers and enterprises to have privacy in their business operations and transactions, not from regulators, not for the purpose of breaking the law, but because privacy is something that people should be entitled to. And because particularly for enterprises, without the assurance of privacy from competitors and from potential competitors, they're not going to participate on public blockchain. So privacy is an immensely important topic, especially on public blockchains, which utilize the core principles of cryptography, but are not by their nature in default private transaction ecosystems. That doesn't mean that privacy isn't possible. And so that's what we want to talk a lot about today. And it turns out that the core technologies for privacy, zero-knowledge proofs, are also some of the key technologies that we need to think about for scalability issues as well. So Barry's going to give us our opening talk. After that, we're going to have our first masterclass of the day at 11:15 a.m. Eastern Time, which is how to build privacy-centric applications. We are all used to talking about dApps, decentralized apps. But we really want to introduce the concept of zApps, right? Zero-knowledge proof-based applications that allow you to have not just private transfers and payments, but private business logic executed on-chain under zero knowledge. And to that end, we have developed a prototype kind of compiler called Starlight, which we have placed into the public domain, right? You can find the early versions of this at github.com/EYBlockchain. And Miranda Wood from our team is going to talk to everybody about how we developed this and what we're thinking. Second masterclass of the day, 12:05 p.m. Eastern. It's all about leveraging the baseline protocol. And I know from my Twitter feed that this is highly anticipated, especially the work that Kyle Thomas from Provide has been doing. He's going to be joined by Sam Stokes from Consensus and Karthik Salapuram from EY. And we're going to talk about how to use the baseline protocol, which is a more general purpose tool set to help companies execute secure business transactions on-chain under privacy. And then finally, our last masterclass of the day today is going to be at 1:10 p.m. Eastern. That's engineering for scalability enterprise solutions. So we spent a lot of time thinking about how do we scale up and manage large volumes of enterprise solutions. We have been doing this for several years. We have learned a lot of lessons, many of them the hard way, and we are offering up sharing those today. And Serkan Estanli from our global engineering team in London is going to be taking us on a deep dive of that discussion. So hopefully there's going to be a lot of excellent content. In addition to that, we've got excellent celebrity guest speakers today who are going to be doing the sort of play-by-play commentary between the sessions. That's not including myself, although I will be on. We've got a couple of amazing folks that are going to be doing this. So we've got Mary Maller from the Ethereum Foundation, which is going to be fantastic. Mary is brilliant. And in fact, we had the opportunity before she went to the Ethereum Foundation, she worked with EY quite a bit. She was very, very good at correcting our math mistakes, I'm told, and we're always grateful for that, even if we kind of felt a little dumb. And so that's going to be amazing. We have an incredibly brilliant Mary. Plus, we have Don Wolpert from Consensus, who's going to be joining us as well. And I'm going to be dialed in. And Arwen Holmes from EY, who's our global CTO. So don't forget, by the way, today is your last day for your proof of attendance protocol token. We have had nearly 1,000 of these claimed. The QR code is going to be visible in the stream. The QR code is going to be visible, especially on the YouTube. We will also put it up on the key slides in between presentations. Remember, it's only live for you to claim while our broadcast is live. So hopefully everybody got some good sleep last night and they're ready to engage. And so with that, and without any further delay, I would like to hand it over to Barry Whitehat to talk to us about the limits of privacy. Barry, thank you so much for joining us.
Hey, no problem. Yeah, happy to be here.
And Barry, you're good to start talking.
Okay, hello everyone. Yeah, thanks for having me. I'm excited to talk. How do I get my slides up? Do you want me to share my screen here or?
Go ahead, Barry. Sorry about that.
Okay, no worries. So I will share my screen, right? Okay.
Yes, you have permission to.
Yes. Okay. Can you see my slides?
Yes, we can. Sorry, just bear with me one moment. This is probably a presentation. Okay, great. Hello, yeah, so again, thanks for having me. I'm happy to be here to talk about all of the things that we can do privately and the things that we can't do privately, because it turns out that it's very difficult to do some stuff privately, and there's like some limitations here. So let's dig in. So like, okay, so what was the first private application? It was like Zcash. So Zcash is basically a way to send payments, transactions to other people where the recipient, where you can't see who is sending what to who, and you can't see how much anyone is sending to anyone else. So the way that Zcash works is that there's like a private place and there's a public place, and you can move from the private place to the public place, and you can move from the public place back to the private place. And there's a problem with this because people don't really think a lot about when they're moving from the public place to the private place or from the private place to the public place. And it turns out that like Mary Maller, along with a bunch of other people, did some work analyzing this, and they found that like people made a lot of mistakes when they did this. So if you look at the graph here, if you see the blue is the withdrawals from the private place to the public place, and the red is the deposits to the private place from the public place. So you can see that there was like a couple of really big deposits that were followed shortly by really big withdrawals towards the end of our graph around like October and January 2018. And like, I think it's fair to say that it's pretty likely that the people who did that withdrawal were also the people who made the deposit of that like big amount beforehand. Like another way to think about this problem is that if you deposit 1.23967 either into a private pool and then sometime later someone withdraws the exact same amount, it's very likely that you are the one who withdrew that, just because it's very unlikely that someone else deposited that much, then made a couple of transactions and withdrew exactly the same amount, especially inside systems where you're not able to like merge and split payments. So this is the first place where we start to find some problems with how much privacy we have, right? When people are doing like deposits and withdrawals, you can start to get a lot of information about who is doing what, or more, you can start having some nice heuristics to analyze who is doing what. Yeah, so this is our first thing. So like what we learned from this is we said, okay, what we have to do is to try and limit people moving from the public place into the private place and vice versa. We want to make as much as we can private as possible. But that comes with a problem. When you start making things private,
you start to change the paradigm that we're used to. So when we make things with cryptocurrency or smart contracts, what we have is both computation and storage, right? We have this kind of very basic computer that we can give programs to, and it can execute those programs. But it also needs to store information. For example, it needs to store that you own a certain POAP, right? It needs to store that so that you're able to like move that and use that later. So there's a temporal kind of execution, but there's also a more permanent storage. So what a zero-knowledge proof lets you do is it lets you hide the computation part of this, right? You can do your computation and you can make it, instead of doing your computation transparently, so you show everyone, hey, everybody, this is the computation that I'm doing, follow these steps, and you will see that I've followed the rules of this smart contract correctly. Instead of doing that, what we can do is say, I don't want to show you exactly what I'm doing, but what I will do is I will give you a zero-knowledge proof that proves that I've done something that's inside the rules of this smart contract. So this works well, and this is what we use to build a whole bunch of different private applications. But the problem is that it doesn't talk about the state, right? It doesn't talk about this kind of the notion of a state where I'm doing something and then I'm saving something, and later I'm going to continue doing that or do something else based upon what I've already done. So like one way to think about this, or one kind of example that you can use to reason about it, is that, okay, so this works well when we have a state that's private to every person. For example, with Zcash, everyone has a state, some state, but that state is only the people who own that coin need to know that state, right? That if I own like one Zcash, Zeke or whatever, I need to know the private key of that information, but nobody else needs to know that, right? Everything else can be like encrypted and shared with everyone else. And I'm not able to block anyone from making any transactions because by hiding my information. That's my information, it's only mine. Other people don't need to know that in order to make transactions. So this gets to be a little bit tricky when we start to think about smart contracts, right? Because as we said before, smart contracts are both execution and they are state, right? So when you don't know the state of the system, things can become very difficult. For example, let's do an experiment and see if we can build like a private Uniswap. So first of all, let's talk about what Uniswap is. So Uniswap is basically an automatic market maker where a smart contract will let you trade from one token to another based upon how much has been deposited into two separate pools of these tokens. And it works very well. It's super simple. It's just like a multiplication and then a subtraction or something. It's very simple. But if we, like what I'm saying here is that if we want to do something that's as simple as this in a private way, it turns out to be very, very difficult. Because if we have a private pool, we're proving that A times B equals K. That's what we need to do, basically. So a user gives a proof that they transferred X tokens, and then that will let them withdraw Y tokens, right? So then we have to calculate K. So K is A plus X times B minus Y equals K. And that's the first state transition that happens in our private pool. Instead of publishing this, we just give a ZKP to everyone. We give a ZKP that and prove that this is correct. But after we do this first transaction, no one knows what A and B are anymore, right? You don't know how much is in A and you don't know how much is in B because we just know that something happened to change what they are, but we don't know what they are anymore. So even if I want to make a zero-knowledge proof that this is correct, I can't do it. Because in order to prove something, I need to know it, right? You need to know what you're proving before you're able to prove it to someone else, right? So, okay, so then you say to me, okay, that's fine. What we're going to do is we're going to reveal K every time. Every time we make a zero-knowledge proof, we're going to show everyone what K is before, what A is before, what B, or what A and B are after the transaction. But then we degrade into the original problem where we have a private pool and we have a public pool. When people are in the private pool until they want to make a trade on Uniswap or in private Uniswap, Then they leave the private pool. We see exactly how much tokens they have of token type A and how much of token type B they receive. And we get to a situation where it becomes very easy to analyze exactly what people are doing, because we have a good idea of like how much is in the pool already, and we can sort of monitor people as they trade. Like, it's probably still better than the status quo, and I think that it's for sure something that we should investigate doing, but it's not the same level of privacy that we're used to, where we don't know how much, we don't know. So what we're used to is that we don't know who's sending what to who, and we don't know how much anyone is sending to anyone else. But in this case, we don't know what anyone is sending to anyone else, but we do know how much they're sending. Right? Every time they trade with Uniswap, we see the amount that goes in and the amount that comes out. We start to see how much they actually have, but not the people. We can't link their different trades together, which for sure is better than nothing, but it's still something that we're not quite, it still feels like we're losing something here. It's not as private as we would want it to be. So now let's talk about some other ways that we can solve this. So some people will say that, okay, so we have zero knowledge proofs, and now we can use multi-party computation with zero knowledge proofs in order to encrypt A and B. So we would have a bunch of parties, these people with the funny teeth, and what they would do is they would encrypt both A and B, and they would do encrypted computations on A and B. They would produce zero knowledge proofs that each state transition was done correctly. But there's a lot of problems with this, because if a malicious group of these people come together, they're able to reveal what everyone has been doing. And if a malicious group of these parties come together, they're able to kind of pause the system. In the worst case, they're able to basically just delete everybody's money or hold everybody's money to ransom until they agree to, until they have paid some kind of ransom or something. So there's a lot of problems with multi-party computation that are a little bit concerning. Another concern is that I'm not really sure how we can select these parties, right? Because if I'm one of these parties in the multi-party computation and I'm doing it to get some kind of financial reward, it feels like I could get a much bigger financial reward by revealing exactly what's been going on inside. So it's just tough to kind of come up with a way to choose these people that you end up trusting in a very important way. Another problem here is that so then you can say that, okay, well, what we'll do is we'll do a multi-party computation, we'll do an MPC, and we'll just have many validators, and like all of them would need to collude in order to reveal privacy. But the problem is that one of them would be able to break the liveness of the system. So basically, one of them would be able to say, I'm not going to let anyone make any more transfers or withdrawals until I get some bribe. So that leads us to, that just feels like very risky. There's this difficult trade-off here that we have to make in order, we have to choose either liveness or privacy. So it just becomes very difficult to make that trade-off. So what can we do instead, right? So one approach is that we can build things with no global state, right? Kind of like what Zcash does, because Zcash has no global state. It just has a user-specific case state, and the same with Tornado Cash. Both of those, there's state, but it's only users need to know that state in order to make state transitions work. And another thing that we would like to be able to do, but it feels very difficult to do, is to make a private stablecoin. So first of all, what's a stablecoin? So a stablecoin is basically a way to, it's a cryptocurrency that's based upon some collateral, is tagged to a constant USD euro value. So what happens is you deposit your collateral, you create this collateralized debt position, and then you basically say, okay, I'll put 1 ETH in, I'll be able to withdraw 65 ETH out, and then I can do whatever I want with that 65 ETH. But if I ever want to get my 1 ETH back, I need to put 65 ETH back in, or 65 DAI back in. So that's how a stablecoin works. And there's also this idea of like But what happens if the value of 1 ETH becomes less than the value of 66 DAI? Well, then what happens is you get margin calls, you get liquidated, and your collateral is auctioned off in order to pay your debt. So if we want to do this in a private way, it becomes very difficult, right? And like, why does it become very difficult? Because we need to know when to margin call who, and yeah, at what price we should margin call everyone else. So this is the idea of like, this is an example of global public state. It's very important that everyone knows this information so they're able to liquidate other people, but it's also very important for privacy that this information is not revealed. Because if I reveal my liquidation price, I'm also revealing how much Ether I put in, right? When I reveal my liquidation price, I move from the private pool into the public pool, and people are able to track each of these actions in order to find out what I've been doing. Okay, so that's why a stable coin becomes really hard. Okay, so that's the kind of scary part of the talk over, and now we can talk a little bit more about what we can do. Yeah, so the first thing we can do is we can do things like Zcash. We can do private transfers. We can do things like Tornado Cash and what Aztec have been doing. We can make these kind of private transactions where nobody knows who's transacting with who, and nobody knows how much they're sending to anyone else. Another thing that we can do is we can include atomic swaps here. And when we include atomic swaps, we're able to make like a decentralized private exchange, which sounds pretty exciting. But the problem here is, like, how do you find your counterparty, right? If you want to make a trade, how do you find someone who wants to trade with you? And this, it turns out to be very difficult, but I'm going to talk about this in a slide or two, I think. And the other thing is, okay, so also I would really like to talk about things that are not to do with financial transactions, because I mean, like, okay, it's interesting to do these things for financial transactions, but a lot of problems in the world are actually to do with like reputation and proving that you have some kind of position in a global supply chain or something like that. There's a lot of other interesting things that we can do, and I'm also going to spend some time talking about how they work. Okay, so let's try and find our counterparty. Okay, so imagine that you have an order that you want to make on a private exchange, and you want to find someone to be your counterparty, but you don't want to tell anyone what you want to trade, right? Because you want to keep it private. So you have this difficult situation where you're like, I really want to make this trade, but I don't know how to ask anyone if they want to trade with me because I don't want to reveal what I want to trade. Excuse me. So yeah, so how can we do this? Well, one thing you can do is you can just ask your friends. You can ask people that you know and trust, or who you have some agreement with not to break privacy. You can ask them, hey, do you want to trade? Do you want to make this trade with me? But that's kind of annoying because you don't really get to trade with every possible person that might be wanting to fill your order. So what else can we do? Well, another thing that we can do is we can do multi-party computation, but not a like scary multi-party computation from above where we have many parties and we're basically trusting them for both validity and liveness. We can do an MPC where we just have two parties, where it's me and my potential counterparty who may or may not want to trade with me. So we can do an MPC together where at least as long as one of us is honest, the MPC will return a valid result, which is okay because I can just say, okay, I trust myself. I mean, you don't have to trust anybody else. So we can do this MPC where we kind of compare our orders in an encrypted way, so that if our orders match, we get a Boolean as a 1, a true flag, and if they don't match, we get false. But this is kind of scary too, because it's annoying because like I can do this MPC with someone and we can get a, yeah, your orders match, and then they can just refuse to trade with me. And there's always going to be that option that they can always have this free option. They can always refuse to execute the trade together. So that's difficult. I mean, we can try and include this we have been thinking about trying to include this as part of the MPC, that like the order would actually get created as part of the MPC. But like there's always a point in the MPC where you can refuse to execute. There's always one person who knows the result and one person who doesn't. But there are ways to overcome that. So yeah, I should probably think about that more. But yeah, MPCs to find counterparties is interesting. But it's also difficult because you have to think of having this mindset of you want to keep something super, super secret, but you also want to do something about it. So it's very difficult to find find both, to find a way to do that. Okay, so yeah, so that's the financial stuff over. I don't think I have any more stuff to do about financial transfers, but there's also all of these interesting other things that we want to do. For example, we have this concept of social graphs, right? Or I guess talking to this group, I should probably say supply chain whenever I say social graph, but like basically supply chain and social graph tend to be the same thing. It's like a network of people who are, or of people or organizations who have some interconnected dependency between each other. And like, so let me just talk in the social graph context, because I'm just more used to talking about it like that. But you can just, whenever I say social graph and friends, you can just replace that with supply chain and customers. Right. So basically, what we want to do is we want to search for paths in social graph, just like Facebook, right? That Facebook has this kind of this reputation system that works kind of well, right? Where it's like friend of a friend is actually someone that you can kind of trust, right? Because you trust your friends, and well, some of them, and so and you can kind of trust people that they trust. So we would like to be able to apply this in other contexts. So like it's easy to make this social graph, right? You can, well, it's not, yeah, it's easy to make it. Like you can just create this map and the connections between different people in it. But the problem is that it's hard to do that privately. So what we can do instead is okay, so let's attend to this privately, and this is going to get a little bit difficult, but hopefully we'll be able to illustrate why it's difficult to build these kind of deeper private systems. So yeah, so I have my social graph, and I make a list of all the people who are connected with me. I have a zero knowledge proof that proves that each of the people on my list has signed a message saying they agree to be friends or connected in the social graph to me. And then what I do is I kind of encrypt this, and I put it on chain. And the encrypted version on chain is just stored there. And when one of my friends wants to find what is searching for another person in the social graph, they connect to me. And first of all, they give me a zero knowledge proof. They prove that they're part of the encrypted set of people I put on chain. I don't know who they are, but I do know that from that zero knowledge proof, I can figure out that they're one of the people on my list. So they tell me, hey, I'm looking to find another person. Can you help me search for them? And I tell them, sure, no problem. Will you just tell me what their name is, and I'll give you a proof that they're in my list or not in my list. And they tell me, no, I don't want to tell you who I'm looking for. I would just like to look for someone. Would you be able to help me? And I say, sure. Okay. So what we'll do is we'll do this kind of MPC encrypted search, where we have a two-party multi-party computation, where as long as one of us is honest, the both validity and privacy are preserved. So we enter this together and we do this computation, and I can do this for each one of my friends. I kind of encryptedly compare it to the person that they're searching for. And when we get to the end of the list, I look at, if we don't have any matches, then I'd say to the friend that's like, okay, I went through all of the people on my list and I couldn't find the person that you're searching for. And they'll say, okay, that's fine, but can you connect me to your friends, and let me do the same protocol with them? And I tell them, yeah, sure, of course. And I create a zero knowledge proof that proves that this person is connected to me. And I ask my friends to perform this search. But these friends don't know which of their friends I am. They just know that I'm one of their friends because I give them a zero knowledge proof. And basically, they start to search through they start to let the searcher search through their list of friends. And yeah, so this is how we do it, and we continue doing this. We continue asking friends of friends of friends of friends until we either get a match or we fail. So this turns out to be very expensive, right? Because we have in this situation, we don't have like we kind of have a global state that we're keeping private, but we have a global state that we're keeping private that's split up between all of the people in this kind of social network. So it becomes very difficult. People have to be online, people have to do this MPC, that okay, maybe it's useful in some situations, but in a lot of others it's very expensive. There are some ways that we can use to improve it, but I think it's still interesting to try this, but it's the kind of thing that it's a good illustrating example about how you end up doing this kind of nightmare stuff to do to deal with this private global state idea. Okay. So, okay, let's talk about something else, something a little bit more fun. So like one thing we would like to do is to do, I mean, it's all fun, but this is maybe a little bit clearer or easier to explain. I wonder how many slides do I have left. Anyway, it doesn't matter. Okay, so yeah, so let's do a private reputation system. So like, what is reputation? Well, reputation is like a way that people have reputation, they can use that reputation to do something, and based upon what they do or how it went, they can either gain reputation or they can lose reputation. So how can we use this? Or how can we do this in a private way, right? Because we have a group of people and we want them to like gain reputation and lose reputation, but we want it to happen privately. So what we do is we come up with this idea of an epoch address. And this is basically a temporal address that people can say, for 1 week, they can send attestations to this address. And at the end of the week, I have to create a zero knowledge proof that I went through all of the attestations that were sent to my epoch address. I have processed all of them, and I have updated my state based upon what I've processed. So every week, I receive several attestations, and every week I make a zero knowledge proof that I have updated my reputation based upon these attestations. So people are giving me like thumbs up and thumbs down. I'm adding up all the thumbs up, subtracting all the thumbs down, and updating my like global list of thumbs ups and thumbs down with what people are doing. So like this could be used in social media. You could use this to have like a social network that's kind of private, where you have upvotes and downvotes, and you don't know how many upvotes and how many downvotes everyone has received. And like this might lead to like some fun kind of social media games. Like like there's a lot of difficulty or uncertainty to do with like privacy on the internet. So this might be this for me seems like a fun experiment that we could do to try and see how privacy and identity will affect these online communities. Because like the question is like, is a Sybil attack what makes it really difficult, discourse online really difficult? So the Sybil attack is just, it's very easy to make many accounts. Or is it the fact that there's no reputation, that like when I'm commenting on YouTube, it's difficult, there's very little stakes for me, right? So anyway, that's a fun experiment that we're working on. I hope I can share more details soon. So another one is that, okay, so rate limit nullifier is basically a way that we can have private, so basically it's private rate limiting. So if you think about the internet as it is today, there's a lot of rate limiting happening. When you go to certain websites, you have to fill in CAPTCHAs, you have to sign in with your email, and like a lot of the reason for this is to limit the amount of actions people can do. Because if you're able to do a lot of actions, that means you're able to if you're able to do a lot of actions, that means you're able to use up a lot of the server's processes. So you're able to like use up a lot of the processes of the computer. You can fill up their hard disk. You can kind of attack the servers this way. So we end up having this kind of rate limiting. And like one example of this is Cloudflare, which is a company that will just limit the amount of traffic that your website can get. And they have some ways to sort of figure out who's doing what and kind of slow people down who are doing too much stuff. So the way that rate limit nullifier works is that we have a group, and you prove membership in the group with a zero knowledge proof, and you also reveal a tiny piece of your private key every time you make a message. And the message can be just like a request website or an instant message that you're sending. A message can be whatever. And every time you're doing this, you reveal a tiny piece of your private key. But if you send too many messages, then your private key can be reconstructed. And people, once someone reconstructs your private key, they're able to like destroy your deposit in some smart contract on Ethereum. So this works kind of well. It's kind of hand wavy, and like to hand wave a little bit more, we can use Shamir secret shares to make it so that you have like a strict 1 message per second limit or something like that. So okay, so that's my talk. I hope I have some time for some questions. I think I do. And Yeah, so basically privacy is hard. The global state, we can't have global state with the same trust assumptions or with like a lot of different tricky NPC things. But there's still a lot of cool things we're able to build. I'm happy to chat more. I didn't know what to do, but I set up this Telegram group so people can join the Telegram group and you can send me some questions there. But I'm also happy to answer any questions here. I don't know how the question and answer part will work, but hopefully someone will tell me.
Hello, Barry. So let's see here. Let's gonna open up to the AMA on Reddit because I think there might be some questions there. So I'm gonna do that right now. And then if there aren't questions there, we'll have a follow-on discussion for you.
Great. Yeah, I'm excited to hear what Mary thinks about this idea in general.
So while we're doing that, let me ask you, Barry, from the perspective of kind of computational intensity, right? How are we headed for a future where we're going to end up using optimistic rollups for everything just in order to keep the cost down? Or what is the way that we're going to manage the cost so we don't end up getting sort of attacked over and over again on the topic of kind of carbon footprint for blockchain transactions, for example?
Okay, cool. Yeah. So, all right, this is a nice question. So the first thing I would say is that like optimistic rollup, zk rollup, whatever scaling mechanism we choose, isn't whatever scaling mechanism that we choose that I think is good will not really help us when it comes to carbon footprint. What we really need to do with to reduce our carbon footprint is to move from proof of work to proof of stake. So there's a nice post on the ethereum.org that talks about how moving from proof of work to proof of stake will reduce our carbon footprint by 99.5%, which is, yeah, I think there's been some articles in The Guardian about this too, and it's a lot of, yeah, it's nice to, I think that the scaling mechanism we use will give us 1,000 times reduction in that, but it's not really going to reduce it by 95%, I think, just because it's so huge.
Okay, and then you think just from a Moore's law perspective, it's going to make it so that it's easy enough for people to implement some of these more computationally intensive privacy tools. I mean, we know we used to melt our MacBooks developing ZKP's tools and running them out. When we did our very first zero knowledge proof-based transfer, we built a little sort of sample supply chain, and we did it for the DevCon in Prague in 2018. We used so much gas, we had to chain together like multiple kind of blocks in order to complete our transaction. And I think we used several $1,000s worth of ETH back when ETH was a lot cheaper in order to get it done, right? And wow, we can't have kind of exploding gas consumption along the way.
For sure. Okay, so that leads us. Okay, so that's like a different question than what I thought you were asking originally. What I thought you were asking originally is like, should we use optimistic rollup or zk rollup, and how will that affect the carbon footprint? But turns out you wanted to ask something more about like how can I do. Okay, you're asking both. Okay, cool. So I answered the first one, and now let me try and answer the second one. And so yeah, it's hard. I mean, so one thing you can do is use optimistic rollup, and that will reduce your gas cost to whatever it costs to make the call, or to just put all the data on chain. That's one thing. Another thing is that what we're doing in the ZKP world, or one thing I'm really excited about is recursion. It really helps with scalability, but it also really helps with privacy. So when it comes to scalability, I think short-term optimistic rollup is going to be the best, but in the longer term, something like zk rollup will probably be the best in the longer run. But it's.
And given the choice, I mean, it seems to me, and I'd welcome your opinion on this. It seems to me that zk rollups are zk rollups keep your transactions on the mainnet, whereas if I end up in a layer 2, I have some interoperability challenges. If, say, I have a token on one layer 2 and I have a smart contract on another layer 2 that I want to interact with, we don't really have, as far as I'm aware, cross layer 2 interactivity yet, except you have to go through the mainnet. So at the moment, that's relatively more expensive. Is that right?
So I think that layer 2 is kind of an overloaded term. It's very difficult to discuss layer 2 because a lot of things it's just hard to kind of. okay, so all of the rollups are they're gonna be effectively off mainnet. Same with ZK rollup and optimistic rollup. There's gonna be this layer of indirection where you move from ZK rollup world to Ethereum world to, for example, optimistic rollup world, right? You're gonna have to do these kind of couple of steps. But there are some ways that we can do this quickly and cheaply. Vitalik has a post about how you can make an exchange that's on one of the optimistic rollups. It kind of watches all of the other rollups, and it will just process every like cross-chain transaction. It will execute them, or else the person running it gets slashed or something. So that's one idea. Another idea is mass migrations, so that you can exit one rollup and enter another one very cheaply. But yeah, there's gonna be some interoperability problems here, and I think it's important to sort of focus on, like, that exchange idea is really nice. I would really like to see that implemented.
So one of the things I'm going to roll into our commentary, and I believe, unfortunately, Mary Maller hasn't been able to join us yet. So one of the things I wanted to do is I'd like you to stay on and give us a little bit of commentary. I've been thinking a lot about what the limitations of privacy are. And our next presentation after this one is going to be with Miranda Wood, and she is going to talk about a compiler that we've been developing called Starlight, which is designed to allow for some level of zero knowledge proof based logic. But nonetheless, no matter how much progress we make, I sort of agree with you in principle. There will be limits on privacy. There will be limits on what can be done in terms of maintaining state and passing information between things that are needed to be private. You can't, if you're an enterprise, as far as I know, find a way to use something like a mixer, because when you're an enterprise and you want to do a contract with another party, you need to have an interaction with them that you sign and you own. You're not just buying a token at arm's length and passing it through an exchange or a mixer. So you have to sign that contract and you have to be engaged. In those cases, right, it's really important to be able to have some other mechanism to preserve your privacy other than just mixing a token or moving it through an exchange, wouldn't you say?
Oh, yeah, that's interesting. So, like, so like what you're saying is that, okay, it's difficult for us to do things like we're doing in cryptocurrency in the traditional world, because a lot of what we're
this is the big reason why we spend so much time on business logic, is because if you and I have a contract, that is between me and it is between you. Now, I can't let my competition see what I'm buying from you and how much I'm paying, but I'm not just passing a token. There are terms and conditions associated with our contract, which means there's shared business logic.
Oh, yeah, I understand.
Now, the other thing that I've been struggling with in the crypto community, and I'd really welcome your point of view, is there is, I think, a misunderstanding about the role between a trusted third party and a centralized intermediary. And I think that people conflate the two, but they're quite different. So if I think about, like, the internet, for example, has trusted third parties. There are companies and entities that issue digital security certificates. They're not monopolies. They don't control the ecosystem, but we do trust them for certain information. And by the way, if you violate that trust, you'll find your demand for your product goes way down. But they're not all powerful like centralized intermediaries. And I think as I look forward to a future on the blockchain, one of the things that we're trying to carve out as a professional services firm and as a firm that does things like audits is a role as a trustworthy and trusted third party that can do things that we can't do on chain with full privacy, and can be trusted to respect that privacy or execute it reliably, but isn't the same. That's not the same thing as a centralized intermediary. How do we do a better job of explaining the difference between those two? Because a centralized intermediary is powerful and poses, I think, kind of systemic risk for the network, but trusted third parties are organizations that can have multiple roles and capacity over time.
So, like, that's really difficult as well. I mean, it seems like you just have a lot of difficult problems for me today.
That's why we ask for your help, Barry. You're one of the smart people we come to all the time for help.
Oh, well, I'm happy to try and help. So for me, it's important to, like, okay, one of the philosophical things that I'm really passionate about is that we should be able to choose who to trust. It's not like decentralization is not about trusting it's not about trusting nobody. It's that you have an option to choose who you trust. And, like, one of the concerns that I have about trusting a third party with information is that once you have a piece of information, you can share that piece of information, and I'll never know about it. That, like, it's very difficult to maintain that level of trust. But I see where you're coming from.
Harry, I think you just gave us like our slogan for next year. Yeah, it's choose who you trust. I love that. I have to give over to our next speaker, but first of all, thank you for an amazing presentation. Thank you for all of the advice and the insights you've given us over the years. We're very grateful. And thank you in advance for our next slogan, which is choose who you trust, which I absolutely love. Thank you. So I'm going to hand it over now to our next speaker, which is Miranda Wood. And Miranda Wood is a member of our research team, and she is going to talk to us about a technology, a product that we've put into the public domain called Starlight. And it is the result of all this discussion that we have had inside of EY about the fact that our enterprise clients aren't just making tokens or crypto assets that they can pass around. They enter into business agreements where the buyer and the seller have to know each other, and they need to execute reliably on chain, but they need to do so without their competition being able to see the business logic underneath their agreement. And so in addition to merely the privacy of transfers and payments, we need some level of privacy of business logic. So with that, I want to hand this over to Miranda. Miranda, thank you so much for joining us. And I am eagerly looking forward to your presentation. And thank you again, Barry.
Thank you very much. Yes, I will start sharing. So today I'm going to be talking about Starlight, which is, here we go. I'm sure someone in the background will shout at me if they can't see my screen. I'm going to be talking about Starlight, which is our prototype zero-knowledge compiler. So this is about taking an ordinary smart contract and compiling it into a zApp without having to know how zero-knowledge proof works. So a lot of Barry stuff actually makes my job a lot easier of explaining what we can and can't do with Starlight. So this is the agenda. I'll be speaking for about 45 minutes or so. So I'll first off start with a brief introduction to zApps and what they are, and how to use Starlight as well. Then we'll move to a more technical overview of how the transpiler works, what a zApp is and how we structure our output zApps, and what's on the horizon for Starlight and what more we can do with it. So Starlight was stood up by our colleague Michael Connor and developed by him and myself in the EY blockchain R&D team. It was released to the public on Monday, which we're very excited about. So it's in the public domain. If you like, you can scan this QR code to go to the GitHub repo, which is open now. It has tons of documentation and examples. So you can look at that right now if you like. I'm gonna leave it up there for a few seconds, but if you miss it, you can go to github.com/EY-blockchain/Starlight, or go to EY blockchain and search for Starlight on there as well. So I'll move on. All right, so zero-knowledge applications, or zApps, bring privacy to blockchains and are really instrumental in bridging the gap between enterprise and public blockchains. So the problem is this technology is relatively new in mathematical terms anyway, and even using a zApp has a pretty steep learning curve. ZApps themselves can take weeks or months to build, and a lot of zero-knowledge experience to build them, which not a lot of people have. It's a very small world, the zero-knowledge world. Or you could spend tons and tons of money on specialist devs to build it for you. So with Starlight, we hope to address a lot of these issues. What it does is it takes an ordinary smart contract. So if you know how to write a smart contract in Ethereum, you can just write one. And then next you mark what you want to be secret. You add some decorators to that smart contract to create what we call a ZOL, Z-O-L, or Solidity file opposed to Solidity. And then you run a single command called Zappify, which zappifies your contract and turns it into a complete working zApp. So if you want to learn about zApps and you know how to write smart contracts, you can use it as a learning tool to make zApps and contracts that you're familiar with. If you want a starting point to make a zApp for your enterprise or something, this provides you with a framework of all the orchestration files you need, Docker containers, startup scripts, zero-knowledge circuits, and shield contracts as well to use. So all you need to know to build and run up the compiled zApp is how to write a smart contract. So I'm going to talk a bit about the user's perspective. So first of all, they would write a smart contract. As I said, they decorate the smart contract with decorators. So here's an example. You just initialize an integer x. If you want to keep it secret, you just add secret in front. You literally write the word secret. And then you can essentially zappify that contract, and Starlight creates a complete zap. This diagram might look a little bit complicated, but we're going to explore it a little bit later. So I'm going to quickly talk about the decorators I talked about. So secret is one of them. That's the most obvious. Excuse me. So whenever you want a variable or state to be secret in your Zap, you just add secret in front of the declaration. And next we have known and unknown. This kind of links to what Barry was talking about as well. We really wanted to keep the extra syntax that a developer would have to add to the smart contract to make it compile into Zap to a bare minimum. But along the way, we realized these decorators are actually really essential to creating a Zap. So known and unknown to do with the concept of editing other people's secret state. So that might sound a bit scary and ring alarm bells for people, but in a lot of cases, we actually do want to edit other people's secret states. So the most obvious way is transferring someone tokens or transferring someone money. So you can increment somebody else's balance, secret balance, without needing to know their balance's value or their private information. So not thinking about blockchain, when you send someone a bank transfer, you don't know how much money they've got in the bank account, you just send them the money. This is kind of the same concept. So if you want your secret state to be not editable at all by someone else, you can mark it as known. So what that means basically is you must know the state's value to edit it, so you'd add known in front of it. If you want to be able to edit a state without the caller knowing it, you would add an unknown in front of it. So in most cases, Starlight can work this up for you, but when we see an incrementation of a secret state, it could go either way. We're not entirely sure what you want, so you need to add these. I'm going to do a quick example, so I'm actually going to go jump into a demo of how Starlight works right now. So I will stop sharing this and share my screen. So this is Starlight in my IDE. What I've done so far is I've cloned the repo and I've done the installation steps. So you can find this all in the repo from the QR code I posted earlier, or under github.com/eyblockchain/starlight. So I've done the installation steps. So let's have a look at a very, very simple example, just illustrative. This contract on the left is obviously not one that's going to be valuable for a real business, but let's just do it for examples. So we have a very simple contract here with a integer a, and there's two functions, one adds to it, one takes value away from it. So let's say that we want to make this secret a secret. So all we have to do is write secret in front of these, and when we add to its value, we want those to be secret as well. So let's put secret there. And again, we have an incrementation. So we need to tell the compiler whether we want anybody to increment the value of a, so anyone who calls this function, or just the person who knows and owns the value of a. Let's keep it simple. Let's do it as known. So only the person who knows a can actually call this. So then next, all you do, as I said, is you've got to run Zapify. So hopefully you can see my terminal pop up here. So you just write Zapify at the argument. That's the contract we have. We go through and it's complete. And there is a warning here, which does make sense. So we have, notice in the contract, we have no references to addresses or anything like that. So the compiler doesn't know who owns the state or who should know about the state. So it will automatically do it as the contract deploy, which is fine. But obviously for real business logic, pay attention to these kind of warnings. And we have a lot of warnings here, which are to do a lot with what Barry talked about, what we can and can't do with privacy. So while you don't need to be like a zero knowledge expert to use this, do take heed to the warnings, and that will actually help you learn a lot more about it. So if we scroll down on the left to see what files we have a brand new Zapps folder that's appeared out of nowhere. And we have one with the name of our original contract. And all of this stuff here on the left is all the stuff that Starlight has compiled for you. So we have setup and startup scripts. We have zero knowledge circuits, one for each function. We have smart contracts, including a shield contract. We have orchestration files, which do all the hard work for you, including a test, and all the interesting zero knowledge proof stuff as well, along with Docker containers and package.js and all that stuff. I don't think I have time to run a complete setup on this. If the zero knowledge setup will take some time. So I've done one earlier. So let's have a look. So if we run the test that automatically comes out of this, we would call add twice, for example, and remove once. So what we actually do here is we're calling the orchestration files, and there are instructions on how to do this and how to work your output zApp all in the README. And all these do is, instead of calling your original smart contract, you would call the orchestration file in Node.js in exactly the same way. So let's have a look at the add one. So this corresponds to the original add function here. Now, just from that single line, we have all of this stuff to do with privacy and keeping everything private and together in the zApp. But you may notice that the only required input is the same input as you originally would to the contract. And that's all you really need to worry about as the user. As long as you call this function with the same value as you would the contract, it will go through all this and sort of make it private for you. It will deal with commitments. It will deal with membership instances in the Merkle tree. It will deal with proving files. It will do that all for you. So I will just show you again the test I ran. So first of all, we increased it by 161, then 35, and then we decided to take away 150. Now, if you are really, really quick at arithmetic, you will realize that that means the final value is 46, which it is here. So we've written the commitments to file just for ease of use. And the last commitment here starts with 2808, and it matches, I hope. Yes, it does. So what this does is it first constructs a commitment for you, which hides the value. It sends it to a zero-knowledge proof, make sure you've constructed it correctly. But if you've nullified a previous commitment that represents the value of A, you've done that properly and the old commitment exists. It puts all that computation together into a zero-knowledge proof, sends that proof along with the new commitment to the blockchain, and then adds that one to the tree. So all the observers know so far is that you've added a commitment to the tree and you've called the function in the contract. Outside observers don't know what the new value of A is, what you've increased it by, and they won't know. So that was a very, very simple example, but we can now that Starlight is released, we can do some more complicated examples as well. So let's have a look on the left at a very simple escrow contract. So with this one, this could actually be very useful. We link up to a public ERC20 contract. You can deposit ERC20 tokens into this contract. You can transfer them between people, and you can withdraw them. So we can compile this contract and turn it into a zApp, and that zApp, unsurprisingly, looks a lot like Nightfall. And one thing that actually Barry talks about a lot in his talk is the private part and the public part. So when you transfer ERC20 tokens from the public part, which is an ERC20 contract, you can't hide that. That ERC20 contract is publicly on the blockchain. When you take the tokens out and put them into another contract, you can't, there's no way to hide that. So here we can't have this amount that you're depositing into the contract, or once it's compiled into the output zApp. This has to be public here. But when we transfer these secret tokens together inside the contract, we can have all the private information as private as we want to. So let's just see what zappifying this looks like. This way. So let's do it again. Zappify -i, and then that contract then. So this will probably give us, yep, a couple more warnings. And this is just what I was talking about. So the non-secret parameter amount. We can't make this non-secret because the compiler knows that this is an external call. But it does warn you that you just can't hide these things that are external calls. So if you deposit something worth 10 and then immediately withdraw something worth 10, it's pretty obvious to observers what's been happening there. But if you deposit something and if a lot of people interact with the zApp and transfer stuff between each other, then from the anonymity set, it essentially hides what you were doing pretty well. So I hope that's been a good demo, showing you how you can use it. Again, there's a lot of documentation and examples on there that you can run at home right now. And we encourage you to do so. So I'm going to get back to the presentation. All right. So next we are going to talk about what we have right now. So I just showed you that we can do everything up to and including an escrow contract. Very soon as well, we're working on what we can do for non-fungible tokens and transferring them privately as well. So right now we can compile combinations of secret integers, secret addresses, some basic arithmetic operations. We can do any number of functions, non-secret states, secret states, and we can do conditionals as well. So if you need to check something equals something else and it requires doing it in a contract, we can do that. We can compile that as well. And quite importantly, we've created a whole error handling system to go with Starlight. So if you write something where the decorator is used incorrectly, or you're encountering errors and you're not sure why, hopefully our error system will pick that up and show you exactly where you went wrong, which is great for learning. But also, if you see a ZKP error, that would mean this is just something that privacy can't do. And that's again what I talked about earlier. So now I'm going to talk about how the transpiler works. So this is actually a very simplified overview of the steps we need to take to transpile a smart contract into a full ZApp. So first of all, what we do is we take the decorated contract, which again we call a Scalability file, and do some quick syntax checks to make sure that decorators are being used correctly. Then we actually remove all these decorators from the contract to create an ordinary Scalability contract. We call this dedecorating. We compile it with Scalability's own compiler called SOLC, which creates something called an abstract syntax tree. So this is a data structure that holds all the code logic in nodes arranged in a logical tree. So this is really useful for us for later. So we take this abstract syntax tree and we redecorate it. So we add back all the decorators that we removed to the relevant nodes. We'll see some diagrams on that later. So now we have something that Starlight can take and turn into a ZApp. So to do that, we take that abstract syntax tree and transform it into 3 new trees. One of them represents the logic in the zero knowledge backend, so that's the circuits. One represents the shield contract, and one represents all the orchestration code in Node that we saw earlier. We also collect some information to make a test file structure. So finally, we use code generation to turn those 3 trees into working code. So what does an abstract syntax tree look like? So even if we take a very simple contract, this box here is, for example, is a whole contract. We have a secret integer x, and then we add some value y to it later. So even with this very simple contract, we go through that process. We create a actually pretty complicated looking abstract syntax tree. So you can see that all the information we need is ordered as stored in the node. So the types, we have integer here, the names, what parameters the function has, and what operations happen in the function. So we do a plus equals x and y here. So when we remove the decorators and compile this vanilla contract, we get this tree, but we don't get these sort of light gray boxes at the bottom. These get added at the redecoration stage. So we add things like is secret and is known. So now we have basically a Scalability abstract syntax tree that we then use to transform. So next we go to traversing. So we travel through this tree and collect all the information we need for the ZApp. So one of the most difficult jobs of Starlight is working out what the output ZApp would look like. Can we build it? Can we preserve privacy? And how it will be structured. So with that tree that we just made on the left, we go through preliminary traversals. So we create these classes that are listed on the right and work things out like how many commitments do we need? How many states do we have? What do we secretly need to prove in a circuit? And what do we need to keep publicly on the chain? Do we need nullifiers in this kind of function? That kind of thing. In the interest of time, I'll go a little bit quickly, but these slides will be available afterwards. If you want to study these diagrams yourself, you can absolutely do that. And there's lots of documentation in the repo as well. So with that information, we create 3 new ASTs. So we just have one output AST here, which is the circuit AST. So that's for zero knowledge circuits in the back end. The other ones are very large. Even this one is quite large. For even a very small input contract with just one line of state change there. So in the original contract, so whenever we call that function, we replace the old value of x with a new value, x plus y. So what Starlight does so far, it has worked out that we need some statements in the circuit. So that means we need private computations in the circuit that we work out off-chain, we prove it that we've done it mathematically, and then we send that proof to the blockchain, rather than doing that computation on-chain and revealing secrets. So from that, for example, we know that we need to do all of these things. So We need to work out a nullifier. We need to do a proof of knowledge of secret key. That's what this stands for the value of X. We need to construct the old commitment, make sure it's constructed correctly, prove it exists, and then construct the new commitment. So all these things are from just that one line. Finally, that tree and the other two trees as well go through a code generator. So every node is turned into a line or character or piece of boilerplate code that fits together to make a working circuit. We use Socrates in the backend. You might have seen some .zApp files, which is a great piece of software to create our circuits, because the code is nice and familiar and easy to use, and you can code the circuits yourself and just compile them relatively easily. So again, I'll move on to the details of what zApps are now, just in the interest of time, but you can look at the slide in your own time. It has some really useful diagrams here to tell you exactly what we have and what pieces of code that we need for privacy. So let's go, what is a zApp? And look at that big diagram that we saw at the beginning. So this is a representation of the architecture of a zApp that Starlight produces from just a single input contract. This is kind of a structure that we use for pretty much all the zApps, depending on what you have in and out, but these key boxes are what we always have. So on the left, we can see that the original input contract has 3 functions. And those functions are transformed into zero knowledge circuits, functions of smart contract, functions of nodes we've just seen. So let's start with orchestration in Node.js. So the user is able to call the 3 functions just as they normally would in the smart contract, but with API endpoints instead of a blockchain client. But it's exactly the same kind of experience. These link to files that we saw that basically do the hard work for you. Each function file will take your inputs, collect any commitments and keys they need from your local database or from the blockchain, excuse me, and passes all the private stuff you need to do to Socrates. That generates a proof, gives the proof back, and then the orchestration file continues with that proof and any commitments you've made and sends that to the blockchain. It also includes startup and setup scripts. So if you don't know how to do a trusted setup in the background, it just does that for you. Run a single script. And that script will create proving and verifying keys for each of your circuits. You don't need to worry about deploying them to the blockchain. That's all done for you. The verification keys get deployed on startup, and the proving keys get stored into a Docker volume. So yeah, let's look at the prover background next. So Socrates has some great simple endpoints, compute witness and generate proof, and those are called for you by the orchestrator. So these circuits, so there's each circuit, so there's one circuit for each function in the original contract. So remember, these circuits in the contracts and the orchestration files will actually are completely custom to your input. Nobody wrote this code that gets output. The compiler writes this code based on all the computations that were done originally. So if your input in function 2 gets multiplied by 3 somewhere, that multiplication is replicated in Node.js and in the circuit if it's a secret computation. We have to copy all of that over. If it's a public thing, it remains in the contract, but we have to keep that in consideration when we do private computations and how these states interact and whether that would leak information. So let's have a look at the blockchain side next. So instead of having your private information on there, you basically have commitments that represent secret states and proofs that represent secret computations. That's a bit of a hand-wavy simplification, but it's a good way to think about it. We verify these proofs on chain and then submit valid commitments to Timber, which is our Merkle tree client. If you listened last year or if you've been following our work at R&D before, you probably know all about Timber and the basic of it. So I'll stop talking about it. So in the shell contract, we have, again, one function for each original function. So that will take the commitments relative to those functions and add the commitments that they need to the Merkle tree and verify the proof relative to that verification key. So I've talked a lot about commitments. So we needed to design a commitment structure that can hide any state change that you can see in Solidity, of course, with that privacy requirements considered. So a commitment basically looks like this. So you hash all the secret information together and put that on the blockchain instead. So all the elements that we hash have been chosen with this in mind. So every state in smart contract is already assigned a unique ID in the background with SOC. So that's really useful for us. Every time the state is referenced in a normal smart contract, Solidity knows which one it's tracking because of this unique ID. So inspired by this, we put the ID in each commitment. This allows us to keep many state changes private without ever having to confuse them, and also manages ownership of states, which I'll get to a little bit later. Next is the state value. So that's the values that represents. It's pretty simple. Could be a number, an address, a string. We just hash it here. So anything that Solidity can handle for now. As usual, we have a public key inside. So the owner of the state can prove with their secret key that they are allowed to nullify this commitment when it comes to it, and privately change the state. And finally, we have a secret random salt, which, among other things, prevents duplicates. So what if we have a mapping or an array? We often work with a balances mapping, like this example here. And this mapping will have a single state variable ID. So say the balances mapping has state variable 7 or something. That won't really work with this commitment system because we do need to differentiate by the two values with different indexes. So the balances of Bob is probably not going to be the same as the balances of Alice. And we definitely need to make sure that we don't confuse them when we add commitments. So when we have a mapping or an array, we use this commitment structure. So instead of the state variable ID, we replace it with the hash, the state variable ID, and the mapping key where we're indexing this mapping by. So if we wanted to hide Alice's balance in here, we would have Alice's address in this part here. So that means we would never confuse the two, and each commitment always refers to a specific state. So with that state variable ID, you might think that there's no reason to think about duplicates, but in some cases, a single state can be represented by many commitments. So this is a discussion about the whole known and unknown thing that I was talking about earlier. So it's about editing other people's secret states. So we want users to be able to send money to other people, to increment other people's secret states, or vote, add their vote to pool private votes. But we don't want them to be able to overwrite other people's states. So we don't want to be able to steal money. So how do we allow this? With the known and unknown syntax, we have that tells Starlight that some secret states are whole. So if something is known, then it has to be whole. If it's unknown, then that state has to be partitioned. I'll just talk about that, what that means now. So with whole states, only one commitment represents a whole state at any one time. Whenever you want to change that state, you have to prove that you know the state, you own the state, and so you can edit it. So you replace that old commitment, you nullify it here, and then you make the new state. You have to submit that nullifier, make sure it's not been added before, and create the new commitment, and that commitment represents the whole state, all of it, hence the name. So with partition state, which is mostly used in things like balances, this pool of commitments here, these can all exist at once, representing a single state. So depending on how your function is written in the original contract, anybody can come along and add to this pool. They can transfer you money by adding their commitment to the pool. That's fine. And only the state can come and take away money from the pool and nullify commitments. Other people can't nullify those commitments. So another tricky problem is how do we work out who's allowed to withdraw funds, or in the case of whole states, who's allowed to edit the state at all? So now we have to think about ownership. So it's a very, very important thing to work out. We have to make sure that other people can't steal other people's secret states. We have to make sure that the permissions that were originally written into the original smart contract are not lost sort of on the way. So taking the escrow example again, this is quite an easy example for human brains anyway, because if you know Solidity, then you know that message.sender corresponds to the address of the person who's calling the contract. And so it's pretty clear that that means that if you own the message.sender address, you own the balances of that address. But the compiler is not a human brain. So we have to teach it to work out and look at it and think, okay, every time we nullify a commitment, as in take away a value from someone's balances, we have to have a message.sender here. So that must mean, this is what the compiler says, that must mean that message.sender owns their own balances. So the user with address X can take away from the state balances X. So that's quite an easy example, but it's good to think about the kind of logical steps the compiler goes through. So this is first of a few extremely fun and exciting notes. There's a lot of irony in that statement. Please don't get excited. So if the payer, so if somebody who's transferring somebody else money, if they accidentally put the incorrect public key in the recipient's commitment, that's not a huge deal because only the payer loses out on the money by making a mistake. If you transfer someone money using a bank account, you would double check their bank details, right? So that's kind of okay in this case, but in some cases, locking the recipient out of using a commitment that's theirs, it can be really bad. So we need to use this concept of ownership to make sure that that can't happen. So with let's look at a trickier example of working out ownership. So we have a contract where we have some kind of mapping that represents customer IDs and a function where you can update the ID. So it might correspond to some private information we don't want anyone else to edit, and it might be some internal company information that customers themselves can't edit. So, well, we know that the ID is overwritten every time, so it's a whole state. But we don't know. We have to use the secret key to prove that you own the state every time you edit it, but we don't know exactly what secret key to put in there quite yet. In Solidity world, if you deployed a contract with this function, you would allow anybody who could see the contract will come along and call this function, which is probably not what you wanted. And so from this contract, Starlight wouldn't be able to work out what the owner is. It would give you that secret state customer ID is not owned warning. So in reality, you'd probably write something more like this, right? So you'd have an admin address or something similar than that, and you'd have a requirement here. Whoever's calling that function is that person, is that. So now Starlight can look at this and go, oh, there's a requirement on a address. That must mean that the owner of the state is admin. So here we don't have that kind of problem of what secret key should we put in there? What should the compiler do? Do we just give it to the deployer? Do we give it to someone else? Because only one user can create and edit IDs. We know it's this address. So that kind of solves that problem. So here's another fun and exciting note. If this admin address is public, so we keep the require statement in the output shield contract, and that checks it in exactly the same way. But if it's a secret state, and so the company doesn't want other people to know what address their admin has, we need to confirm that that address corresponds to some zero knowledge key that we put inside the commitment and prove the caller owns that key inside the circuit, which is a much more tricky problem, actually. All right, so I'll move on to accessed states. So again, this is kind of similar to ownership in that we have to check that somebody is essentially not lying, to have to check that they own a state in order to open that state, check its value, do something with that value, right? So this is a very simple example. Again, on the right, we have two functions, one sets A and one sets B, they're both secret. So set B is really simple. You just set B to be a new number. But set A, you have to check first that the value you're setting A to is larger than B for whatever reason. But B is secret, so we can't keep this require check. We can't keep that in the public shield contract. We have to put that into the circuit. But then how would you access the value of B? This is like what Barry was talking about. How do you know that? So first of all, the compiler works out, well, the owner of B has to be the owner of A. And we need to extract the current commitment, open it, see its value, do this check, and then make sure that this commitment is the current one. So let's go quickly through that process. So these are some of the inputs that will be sent to the zero knowledge circuit from just a small contract. So for some notation here, each C is a commitment, CA is a commitment for A, and CB is a commitment for B. So we have two commitments for A. So we're calling this A here. So we need an old commitment to prove that we know the previous value of A. We're nullifying it, replacing it with a new one, which is the middle one here. We also have to have the current commitment for B, because we need to prove that we know what B is, and indeed that A will be greater than B. We also need to submit nullifiers for these. So the red box is here. So we submit a nullifier for the old commitment for A, because we need to nullify it. And we also need to submit a nullifier for B, not because we're going to nullify it, but we need to prove it's the current commitment. We're using the real current value of B. We're not using some previous value that's currently been nullified, and we're not basically lying about what we're saying B is. So the process that the zApp currently would go through if we compile this for Starlight is the circuit would check all these commitments exist, apart from the new commitment, which doesn't exist yet. It checks that all the commitments input are constructed correctly by reconstructing them. and doing the same thing with the nullifiers. And finally, it does that check. Is A greater than B? Is the input that we're saying A is going to be, is that greater than B? Once that all goes through, we send the proof and these commitments to the contract. We check that none of the nullifiers have been added to the nullifier list. We check that the Merkle tree roots match, because we've used the Merkle tree root in the circuit to prove that they exist in the Merkle tree. So we have to check that on chain to make sure that's correct. And then the next thing is we nullify the old commitment of A, so we add the nullifiers to the list, but of course we don't add the nullifier for B. We're not changing that, we're just checking that the value of B is correct. So that might ring alarm bells for those ZKP people, because we have to share publicly the nullifier for B to make sure we're using the current value without actually adding it. So this can be considered a bit of an information leak. It's not critical, because nobody can come along and use this nullifier to actually nullify B without being instructed. You need to prove that you're in the secret key inside the commitment for B. So only that person can actually do that. But they do know that if they're observing the contract, they will know when B is changed next, which can be considered a bit of an information leak. So to prevent this, we have looked at other accumulators like polynomial commitments, for example, where a user can submit a non-membership proof showing that this nullifier is not yet in the set without actually sharing that nullifier. So these are just some of the considerations that we've had. So that brings me nicely to what we can do next. What are the future possibilities for Starlight? So while we have the zero knowledge concepts down, and we have sort of built this protocol to turn something into a ZApps, as long as we can keep those things private, we are not compiler developers. We don't compile languages into another. We are the kind of people who, build these zero knowledge protocols. So there's a lot of stuff here that we have already the thinking done, but not the coding quite done yet. So a lot of these things we've already talked about. So like sharing secret data is a big one. So when we edit someone else's secret state, it's critical for them to make sure they know about that edit and they can open that commitment. We would need to encrypt the secret data and broadcast it to them, make sure only they can do it. So we would need a key scheme to convert between not only your Ethereum key, but also your Ethereum address, plus the key inside the commitment, and possibly a different kind of key that would be efficient to use in encryption, because we'd need to prove that inside the circuit, which might cause a lot of constraints, a lot of slowing down. So we have obviously releases to the public domain. We would love to have some feedback, some contributions about how we can do this and how we can go about this from perhaps people who are compiler developers or anyone who would like to get involved, anybody with just blockchain knowledge who would like to tell us how it could be easier to use and how we can improve this further. We also have a lot of longer term plans we've been thinking about, so we can upgrade the background systems to the newest technology. So we already talked a little bit about polynomial commitments and doing things like that. And we also talked a little bit, we also thought a bit already about recursion. So Barry mentioned this. With recursion, we would also be able to hide which function is being called by hiding the proof of computation within another proof that shows I'm choosing one of these functions to compute for, but I'm not telling you which one. But again, that requires a large overhaul of the thinking underneath and a lot of coding and a lot of mathematical thinking as well. But these are the kind of things that we've been thinking about already and the kind of things we'd love to expand on with a bit of industry help. So again, here's the QR code, here's the link, go forth and Zappify with Starlight. We would love contributions, discussions, criticisms. Please come along and you can start issues, you can start discussions. We'd really love that. So yeah, that's all from me. Thank you very much. I think I finished a little bit early, so bye.
That's all right. I don't see any questions currently in the QA submitted from the audience. So what we'll do is just extend the break and the commentary, and we'll cut to that now.
Sounds good. Well, thanks everyone for listening. Do you have some Q&A? If you have some Q&A, please put it in the Zoom Q&A or the YouTube one, and I'll take a look and see if I can answer this. Thank you.
All right, and up next we have our block talk with Mary and John. Take it away.
Hi, John.
Hey, Mary, how are you? Good to
I'm
see
okay.
you.
How are you doing? Yeah, good to see you. So,
I like the grass. You look like you're in that movie Ants.
yeah, I probably should have chosen a more plain one.
So I love that. Yeah, I've been tuning in off and on all week, and my colleagues at Consensus have as well. And every now and then people will say, "Come on, jump in. There's something really cool." And I was just doing that for this last segment. I thought that it was outstanding and it was real eye opener. I'm hoping Miranda can stick around. I'd love to get more. I have lots of questions. Q&A might have been pretty deep for a Q&A, but I've got tons of questions about that.
I mean, I'm just.
I'm here. I can answer for you.
I'm sorry.
Sorry, go ahead, Mary.
Oh no, I was more saying as I find it really exciting that you're working on this in general. Like when it comes to things which are a real blocker for getting zero knowledge being more widely used, then definitely usability is like top of that list. And so to see that you're actually there, you're actually tackling it, you're actually thinking, what can we do in order to take this complexity and make it back end? Yeah, it's impressive.
Thank you. Yeah, I really appreciate it. That's exactly what we were going for.
Yeah, very often I'll find ZK people that know the ZK can't explain the ZK. And you got both, and so now I'm exercising my terror of Paul Brody coming after me if I try to poach any of his people. So I'm like, nope, can't call Miranda. But amazing work. I'd like to know. I mean, so I come from Watson. I worked on the Watson stuff. I wasn't on the research side, but when we got going with it, finding ways of putting AI to work, and I always think about putting stuff on on blockchain. I've often said it's a digital nudist colony, right? Everything on there, everybody, anybody with a node can see. And that means that if I've got a good AI, I can start sniffing for classifiers, right? Or a good ML system. What in Nightfall, and we worked a lot in the baseline protocol community on with Nightfall. You do have not only the setup from a ZK perspective, but also you do have to post that the logics on chain and then put it into the Shield contract. What kind of exhaust are you putting out with Starlight that I might have to worry about, just in terms of, really just basic morphologies that might be able to give me away in light of AI?
Yeah. No, that is a good question. It's quite similar to Nightfall right now. I think Barry covered this really well. Is that yes, you can compile a zApp with this, but you do need to have those considerations there. Like if you don't have a big enough anonymity set and you're taking something from the public place to the private place, you still need to consider that it's going to be pretty obvious from observers that if you're the only person doing that, it's pretty clear that you're putting this stuff in, taking this stuff out, who you are and what you're doing with it. And that still happens with a lot of output zApps here. In some cases, not so much, because you can do something sort of kind of entirely in the private place. Not entirely, I'm being a bit hand wavy, but you can sort of trade things together which are entirely created from the zApp. It's probably very similar to Nightfall, yeah.
Yeah, that's why we do all of our stuff off chain for that reason. Mary, go ahead. Sorry.
One of the big issues that sort of comes up time and time again when you're writing these zero knowledge circuits for things you can get wrong is overflow errors. What happens if you try to add two things together, but they go over the total size of the field that you're allowed to work in? How would you say that Starlight handles that?
I think it handles it okay. But that is, yeah, I understand that. That's a big problem for us, especially because obviously with smart contracts, you can add and take away stuff. A lot of warnings basically, and say when you're decrementing, this can't go below 0. When you're incrementing, this can't go below whatever the prime field is, which is huge, but it's still a consideration. So we do have overflow errors that kind of thing in the zero knowledge circuits. But yeah, it's another sort of privacy restriction in that we can't deal with negative values in the same way that Solidity might be able to. So there's a lot of warnings there, but definitely something to be worked on. Maybe we could.
How, with Nightfall and with what we've been doing with baselining, to generate a zero knowledge circuit, it's still a practitioner's art, and to get to be able to atomically go in and just write Solidity and then say, yeah, secret. I thought that, boy, that just, I'm trying to resist getting too excited, because it seemed like something that could be very rapidly adopted by the rank and file of blockchain developers in a way that stuff that we've seen before hasn't been. So, man, this could be it. I mean, this could be the thing that really, I'll be watching the forks and clones off of that repo pretty closely. What needs to go on? I mean, how far do you think you are before you're production ready?
It's difficult to say, but there's a lot of complicated business logic that we still need to allow to happen in there. So, like you said, writing a zero knowledge circuit is very difficult, and so taking that logic in Solidity and turning it into what we use as Socrates code, it can be very difficult, and we can't do everything. So it's hard to say. I think in terms of what Solidity does, we probably got about only 30% of what Solidity can do sorted. But I reckon there's at least maybe 20% that Solidity can do that privacy just can't do, like based on what Barry talked about earlier.
But that may not be a deal killer for a lot of enterprise applications. So the question is, how long before I, as a CIO of a major company, or even an SMB that deals in a fairly serious kind of part of business, how long before I can be confident that if I'm employing this, I'm not going to I'm not going to regret it later. Even if I constrain the use to a specific, to something that's really well known.
That is a good question. I think, again, it is hard to say. We would really like to work with the community to develop this more, because, again, we're not compiler developers. So trying to work with people who are compiler developers and know a little bit more about this would be really great. I think one of the great things that we have done is create a really robust error system which warns you about as many things as we as KP developers could think of, like the anonymity set, like underflow errors. So as long as you read those, you should be pretty comfortable in that, okay, I'm considering those, and that's how I'll use the output zap. So yeah, I guess that's the only answer I can give right now, but yeah.
What do you think, Mary? Is this, from your perch in the Ethereum community and the foundation, what are your thoughts on where this could go?
On where this could go? I mean, I'm very much hoping that people are going to sort of look at it and be there like, okay, if I want to be able to trade privately, then I don't need to go and get a specialist developer, of which maybe there only exist a very small number. I can just find someone that is able to work with this compiler logic in order to come up with something which I know is going to be safe, I know is going to be okay, I know isn't going to have me thinking that I've hidden from the world, I don't know what stocks I'm buying, when actually it's told the whole world that I'm buying these ones because I'm the only person in the anonymity set, or I'm one of 5, and I first take myself into the private setting, do my stuff, but then when I come transparent again, it's like there's only one outcome that could have been. Like, I think having some reassurance that those kind of issues just aren't going to come up would make a huge difference.
Yeah, I think yeah, that's right. If we can, if it's as simple as saying, this component is secret, that would be, this function is secret, that function is secret.
It's never going to be completely secret. It's just sort of warning you where you need to be careful and where things are okay.
Do you think like inventory moves and things like this, right? Where a company really doesn't want its competitors to know about its inventory state, but you want to be able to have nicely compartmentalized, verified workflows. That's what we think about in the baseline community is, are you able to work with a set of counterparties and have a whole bunch of counterparties in work step A, all visible to each other, but then, the next work step is just bilateral between, two, and another work step later on. And there's not even awareness, 25 steps in, that there was anybody involved in step number two, or that there was a step number two. I mean, these kinds of compartmentalizations are essential to enterprise. And, if I have a contract, I'm a pharmaceutical and I have a contract with my wholesaler. Downstream from that, they have a contract with the pharmacy. My contract as the pharmaceutical is not only confidential, its existence is confidential. It's not, CVS or the pharmacy is not even supposed to know I have one. So these kinds of things matter for that, right?
Yeah, they definitely do, both for privacy, and I think what some of the issues you were discussing there were more anonymity issues. You're not just trying to talk about what you're trying to hide, you're trying to hide who you're even talking to, and that's,
or that you're even talking.
And that's more complicated again.
Yeah.
Would you say that that is something which Starlight would be able to handle, or is that future work?
I would say that's future work. It is a very tricky problem, as you say.
Yeah, I mean, it's current work in baseline. I mean, that is so.
We definitely need to wrap up, by the way.
Oh yeah, right. Well, the last question, but maybe we'll take it offline. Is do you have a sense of what the relative cost of this stuff will be? What is the simplest Starlight event that made secret? How much do you have a sense of how much gas that will cost?
It would still be quite expensive at the moment because we don't have an optimistic or zCloud backend. But in the future, we'd like to implement that, and we can take that offline as well.
That's a great answer. Thank you. Mary, Miranda, it's great to see you both. Moving on.
Thank you both.
Thanks, everyone. Up next, we have Leveraging the Baseline Protocol with Karthik, Sam, and Kyle. The mic is yours.
Hello, everyone. This is Karthik Soripuram. We will be giving a presentation today on leveraging the baseline protocol. We'll start off with introductions and we'll go over the basic components of the baseline protocol, followed by some of the reference implementations, and finally a live demo as well. To start off, my name is Karthik Soripuram, play the role of solution architect and platform engineer at EY. And also play the role of a member on the baseline steering committee and actively focus on platform engineering efforts and infrastructure efforts around commercializing privacy technologies. Over to you, Kyle. Sam.
Hey, Kyle Thomas, founder and CEO of Provide. Also TSC member, as Karthik mentioned, for the baseline protocol. I'm still getting over some allergies. Sorry for that. Hopefully won't have to hit the water too often. Looking forward to sharing all that's going on, in the baseline community from a tech perspective, and also, we have some exciting stuff coming up with Oasis Standard, and happy to be here. Thanks for having me.
Hey everybody, Sam Stokes. I'm a software architect at Consensus, and also a maintainer of the baseline open source repo, along with Kyle and Karthik and several others. So happy to be here as well. Kyle, if you wouldn't mind putting that in presentation mode, please.
I do know how to use PowerPoint, I think.
Just go to slideshow on top.
Where?
Slideshow.
Where? I don't see it. Where's it at?
Go to the bottom right hand in that small toolbar. You see a little podium icon. Yeah, there you go.
All right, cool. I think in full screen it does something different. That's my excuse.
All right. So I'll start off with the introduction and background for Baseline Protocol. So Baseline Protocol is something that began as an initiative between Consensus, EY, and Microsoft, and was launched into the public as an open source contribution around March 2020. The initiative was announced and made as a part of an Oasis open source project as well, and it was supported by 14 other funding companies. Baseline protocol essentially is a set of techniques that must be implemented in a standard way across different systems. So this, when we talk about a standardized set of techniques, what we are primarily referring to is a way for different organizations and entities to use public Ethereum or the mainnet as a common frame of reference for synchronizing data, for synchronizing business logic in a private manner in such a way that any party who is interacting with any other party, their information is not made public, and is also made ensured that any logical components that are in play are also made private as a part of it. So as part of this, we started off with a POC called Radish 34, and this was made public in March. And since March 2020 until now, there have been a lot of exemplary contributions to commercialize or to make this stack of various services that was introduced by Radish 34 into something that is production grade, something that is reusable, and something that a variety of companies can also interact with one another. We'll be going over some of the details of the various components, but at a high level, the various components are the zero knowledge library, much of the concepts of which we have gone over in the previous discussions, the point-to-point messaging piece, internal messaging across within the organization itself, and finally, a way to ensure that the off-chain data and on-chain data are in sync by using something called Merkle Tree Manager. When we started off with Radish 34, we used Socrates as a standard way or a library for codifying any form of zero-knowledge circuits and compiling them and converting those proofs into something that is verifiable on the mainnet. And as it evolved, we have been using BRA1 and BRA2, the reference implementations. We've gone forward with replacing, or rather adding components or adding abilities to integrate with NARC, and specific custom implementations like provide privacy as well, which details of which we'll be going over in the presentation today. From a point-to-point messaging system, we started off with Whisper, the gossip-based messaging protocol, to now we are more or less using something called NATS. NATS is more of a point-to-point, somewhat centralized system, but ensures guaranteed delivery. This is something that we'll also go into in details as in the later part of the discussion. Internal messaging is something that we leveraged where entities within the organization, or rather users within the organization, how can they communicate with one another. While Whisper and NATS play the role of inter-organization communication, there is also queuing systems and various messaging systems that organizations internally use. When we started off with Radish 34, we used something like an open source framework called Bull.js. And BRA1 uses NATS, and BRA2, as Sam will cover later on, uses NATS, a combination of NATS and Kafka. And finally, as part of Merkle Tree Manager, I think in the previous discussions, you have heard of EY Timber. We used EY Timber as part of Radish 34, which was made more stable and more commercializable by using provide privacy and the commitment manager, things which will also go into as part of this presentation. All right. Some of the main before we step into the libraries and the various components of Baseline, just wanted to touch upon some of the key considerations for privacy on the mainnet. The four main pieces over here. The first piece is about security. When we talk about security, we refer to data that is enterprise legacy data, which should not leave the legacy system. We should not leave the legacy systems when there is any communication between organizations. I.e., when organizations are leveraging the mainnet, any data that is internal to these organizations must be made secure, or rather must be masked away from any other entities on the system. By extension, any transformations or mutations that happen to the data during the point of interchange or during the interchange also must remain hidden. The second concept is around data consistency. We need to make sure that there is a consistency of information across multiple systems. We achieve this using state accumulators and Merkle trees, which is something that we'll also go into as part of some of the reference implementations today. The main aspect of using mainnet is to ensure that we can use something like smart contracts or programmable logic to verify data consistency while keeping the data hidden. In addition, we need to be able to ensure that any form of implementations on mainnet can be extensible to changing privacy techniques. Like the various techniques that you must have come across are like the ZKP proof-based privacy techniques, and also other form of privacy techniques like under the ZKP systems like bulletproofs and so on and so forth. Finally, when it comes to scale, we need to be able to extend the private state to other entities. So in this manner, it becomes important that any zero-knowledge proof that is composed or created needs to be extensible across a different business process for enabling proper tracing of the proofs as they change state, or as data changes state for that matter. We can go to the next slide. All right, so I'll go over briefly the components that are leveraged in baseline. So as before, we have a few core components that are primarily essential for ensuring that any two enterprise systems or any two entities are baselined. When we say two enterprise systems are baseline, what it means is that any data and business logic for any business process that the two entities are interacting with, there needs to be consistency of data, the state, the business logic, and also making sure that any of these interactions are hidden under privacy, under zero knowledge. So to that extent, we have the following components. We have API, which is essentially more like a JSON RPC module, very similar to many of the RPC modules that are out there for interacting with Ethereum clients. But a baseline API stands out in the sense that it also provides integrations with key vaults, provides integration with custom authentication providers, and also custom vault provisions where specific zero-knowledge keys or zero-knowledge based proving or verifying key pairs and so on can also be integrated as part of the stack. So API consists of all these adapters, for integrating with the mainnet itself. And in addition to the mainnet, it's also important that the API acts as a gateway to the rest of the stack. And in that sense, we use API as a standard mechanism or API as a standard gateway rather, to interact with smart contracts, with the messaging layer, and with the privacy components as well. With that, we go into the contracts. Contracts is basically the smart contracts. And here we make sure that the smart contracts that we are developing or that are being used are something that we can rationalize across multiple organizations. The way we do that is by using some of the standard ERCs, like ERC 1820 as an enterprise registry for identifying different organizations. And we also use some standardized shield and verifier contracts. When we say standardized, we have taken some of the components of inspired by Nightfall, inspired by Zcash, and various other similar protocols. And we have come up with a shield contract interface that is rationalized or that is registered with the global organization registry. In this manner, using the organization registry and an extension to DIDs, which Kyle will go over in SBRI1, using these DIDs as identifiers for different organizations, one can not only identify the other organizations, or an entity can not only identify the other organizations, but they can also identify the particular shield contract, the verifier contract, and for that matter, any zero-knowledge proof-based circuit or RNCS circuit that is being used for composing the different proofs. You have messaging. Messaging API covers a standard set of standard set of endpoints to be able to conduct any form of point-to-point messaging. In this case, this messaging is tied back to API to ensure authentication using JWTs. But for that matter, it can be extended to any other form of authentication as well. The main point of messaging is that messaging ensures that any business process can be linked to a corresponding entity, their corresponding shield and verified contracts on the mainnet, and also the corresponding circuits. So when a message is being sent between organizations, counterparties are able to identify which business process it's aligned to, which particular functionality in the shield contract they're referring to, and by extension, which Merkle tree also, or which form of Merkle tree composition or aggregation they are referring to as well. And finally, privacy is a component which covers the details of privacy is a component which treats all the different abilities to interact with the zero-knowledge proof-based circuitry. Like, for example, ability to create circuits or a compiled circuit, set the circuits up, and also generate proofs. We have adapters for all of these components in such a way that we can flip over from Socrates to NERC, or right now we are also looking into extending it for other provisions like Plonk as well. With that, I think we can go to the next slide. So before I flip over to the work groups, I quickly wanted to touch over privacy management and how we address this in baseline. In a nominal setup, we have Alice and Bob, two entities who can be assumed to have the entire set of baseline stack stood up or initialized on their respective instances, which would be the set of the APIs, the messaging, the privacy, as well as the contract integrations. So this stack is something that is initialized as part of work group creation, which is what we'll go into next after privacy management. So the assumption here is that Alice and Bob have their participant stack set up in such a way that Alice and Bob can identify each other on the mainnet using org registry. And once they've done that, Alice intends to send a document or send any form of a private information or private datum to Bob. To be able to do so, Alice compiles and provisions the circuit by writing a zero-knowledge proof-based circuit like an R1CS circuit, and then storing that particular circuit along with the metadata of that circuit and its linkages from an AST perspective, similar to the previous presentation. We look into how the different ASTs of the smart contracts can be linked back up to the different circuits, and we just nominally identify a particular AST function to a particular circuit function, and then we use that sort of linkage to be stored in an off-chain store. Then we go into the setup piece, where as part of setup, we use again the ZK snarks type setup as part of this. And this generates the proving key and verifying key pairs. A key part of this piece is that setup can be considered as one of the point of the security vulnerability, mainly because of the problems associated with getting rid of toxic waste, and also around issues with having multiple parties interacting to provide a nominal set of proving key and verifying key pairs. And it is also important that this setup is not just run by one person, but it can be run in a multi-party scenario, and baseline plays a perfect playground for this. And so as part of setup, we create a proving key and verifying key pairs. Again, since we're using the baseline stack, once this is set up, the corresponding proving key and verifying key pairs are tagged to the circuit and hence to the Ethereum address and so on and so forth. Once the setup is done, the artifacts are generated, which include the R1CS based R1CS systems based circuits, the proving key and verifying keys, and also the Solidity API. Once these artifacts are published and are made available to the various parties, Bob the counterparty can then, as a point of joining the baseline stack, can retrieve the information instituted in these various proofs to then deploy to the verifier smart, to then deploy a proof or deploy a verification to the verifier smart contract on the mainnet. So this is how privacy management works today, and we'll be in the baseline stack. And we are continuously working to improve the way setup and artifacts work so that we have a nominal system or a good linking system for linking a certain business process to a certain proof, to a certain circuit, and so on to a particular identity as well. These are some of the considerations that we have strongly taken into account for implementing in production any form of zKP system. In this case, we have taken a particular zKP system in play, which is like Socrates or NARC. So it's effectively a zk snark-based system. And the efforts of the community were in making sure that the parts of the stack are repeatable, reusable, and can be integrated back into enterprises. Finally, I just wanted to quickly go over an example of a baseline circuit. Given the various business considerations around making sure that data is consistent between enterprise systems and that any data that is shared is also hidden under zero knowledge, we've although there can be many different logical components, or for that matter, different types of business logic that enterprises go through, we've tried to come up with one base circuit, which essentially covers 3 points. One is to ensure that there is a proof of knowledge, to ensure that any kind of document that is being published or that is being shared is consistent between the participants. Then we also ensure that there is a proof of knowledge of signature, which also is something fairly established. And we use EDDSA-based mechanisms to essentially ensure that any signature or any signed object is actually related to the original entity or the signer, and it is also referred for the intended party as well. Finally, for ensuring that there is consistency of data, we calculate the roots of the Merkle tree off-chain, and we link them up to the corresponding Merkle tree leaves on-chain. The way we handle this is also inspired by EY Timber. The protocol to ensure, or rather the mechanism or a layer 2 mechanism to ensure that any off-chain data can be linked to on-chain data by using sparse Merkle trees. So a combination of these 3 circuit diagrams, the combination of these 3 circuits is essentially what ensures that this forms a strong basis for further baselining. What that means is essentially, with having this as a basic setup, any future proofs or any logical proofs that are constructed can be constructed on the basis or composed on top of this. So this acts as a basis for standardization of data and private elements across different entities. With that, I'll pass over to Kyle.
Thanks, Karthik. So sort of taking a step back from the privacy, sort of the setup, and really being able to make use of the baseline protocol. Taking a step back from that, we look at sort of how we get started. How a work group sort of gets formed. And really, it happens sort of like how you would expect from like Slack. If you invite someone to a service, they get an invite, they can click a link. We envision sort of the same process as playing out for baseline work groups. Once an organization is registered in the global in the on-chain registry using the iRegistry interface in the core packaging, that organization basically is associated with an Ethereum address it's actually never used to sign transactions. It's just used to look up that organization in the registry on chain. And so essentially you can think of that as a DID of sorts. And when an organization receives an invite and they basically say, okay, I'll join this work group, it's a verifiable credential that they receive. And essentially they use that verifiable credential to connect to the party that invited them. And we'll show this here in a bit. So if Karthik was to invite me to a work group, for example, He would sign a verifiable credential that I would then use. If I decided to join the work group, I would be able to directly connect over NATS to Karthik and say, okay, I'm in, I'm going to join, but I need to sync. I need to sync a bunch of data about the work group so I can participate. And this could be, certainly the circuit artifacts, the binary R1CS artifacts, any proving verifying keys that could be needed for that participant. So that's sort of how it fits into the overall picture of the privacy setup that Karthik was talking to. I think it's just important to note that the credentials exchange just simply happens out of band. So an invite happens, and a VC is issued, and then that VC is just handed to counterparty, but the invited party out of band. Moving on from that. So once you've got your work group sort of set up, you've got a couple of parties in there, that have joined. You have circuits that are deployed at each respective customer, organization's stack, or their premise or their cloud, however they decide to deploy that. At that point, the baseline protocol can sort of proceed, and there's going to be a set of documents that are, or business objects that are of high importance, to keep consistent between parties. So if you think about such a document, being a record in an ERP system, when any upsert of that record or that document type takes place, the ERP system will basically trigger, the way it's currently implemented, will trigger an outbound baseline protocol message, and it's essentially attempt to resolve the baseline context, which means like if there's already a workflow in progress, essentially the state transition would be applied against that existing process. For example, the latest root, Merkle root, could be resolved as part of this on chain if that process had been exited to layer 1 in the past. Once this sort of process, it represents an atomic state transition in the baseline protocol, essentially, such that if the transition is not compliant with the circuit, the logic in the circuit for that work step. So essentially, if this delta is going to make the business process go off the rails, then it won't happen. And so at that point, if the circuit would, actually break and not proceed, the ERP system would receive, it's not pictured, but the ERP system would receive sort of a notification so that like some user-friendly error message could be shown. Assuming that the atomic update, is deemed to be acceptable and compliant with the circuit, there will be a proof recalculation that happens, and then the hash of that proof that's generated in this, by way of leveraging NARC, for example, it can either be shielded on chain or deferred for later in L2, which and then potentially used later in a roll up or some other similar transaction. Karthik, I know you probably want to add a little bit here.
Well, sure. So one of the main aspects here is the data availability, which is something of a concern or an issue in most of the layer 2 designs, which is making sure that the data that is shared between off-chain systems is in sync on-chain. While we use, this is where we use something like EY Timber, or we started with using EY Timber, which provides a great basis for synchronization of off-chain routes in the Merkle tree to an on-chain route. So while you can have a full-blown Merkle tree that is stored off-chain, you can have a sparser Merkle tree that is stored on-chain. And simplistically put, this is me putting it simplistically as to how EY Timber works, but the idea is to make sure that we use, or the idea is to use sparse Merkle trees as a way for optimizing how data can be, data sharing is highly available on the mainnet, where usually we face a lot of latencies with data being available across multiple systems. One of the considerations over here around moving from one proof to another proof, or say creating one proof and recalculating the proof on top of it, while there are many proof compositions or proof batching mechanisms that we are also looking into, one of the alternative approach that we have taken here is to take all the different proofs, or rather generate the different proofs from different parties across the different circuits. And these proofs that are generated on L2 or off-chain are something that can be signed, and then in a roll-up circuit or a bridge circuit that we call between, say, enterprises' legacy systems or their L2s and the mainnet, we use the roll-up circuit as some, let's say, a placeholder for the moment in terms of composition of proofs to sign the different individual proofs and verify the multi-signed proofs. So it's more of a workaround that we are looking into at the moment to ensure that multiple off-chain proofs can still be synchronized by using and multiple off-chain proofs and their corresponding Merkle trees can still be synchronized to, say, a unitary Merkle tree on the mainnet. So that's where we use something like, or at least we have been using something like a roll-up circuit for the state availability and validation.
Thanks, Karthik. Yeah, I think it's interesting because if you think about what an L2 is, the characteristics of it, you have to have off-chain consensus rather among your parties, which is really what we need in the baseline protocol before something becomes more final on chain, which is I look at that as like when that happens, there's some sort of tokenization event or some other financial instrument that's going to be usable as a result, as the output of a baseline process. Tokenizing the output of that process really, in my opinion, should happen around the time when there's some sort of financial instrument that can be created from it. So perhaps a good strategy would be to sort of aggregate all of these hashes of proofs in L2 until a certain inflection points, depending on the business process. Sam, did you want to add anything to this slide here?
No, I think you guys covered it well. Okay.
So we'll go into the BRIs. So baseline reference implementation number one was one that we at Provide created, and it essentially was we were in the right place at the right time, I think, in terms of the maturity level of our tech stack. After having been in the enterprise blockchain space for some number of years prior to March of last year when Baseline came out, and so what you see here is the incremental improvement in the Provide architecture in the context of we added a vault, basically, right? We added a key management system for that with a focus on sort of advanced privacy and messaging. Like we want to be able to add add curves sort of as we wish, instead of being beholden to some other platform. So that was sort of the decisioning around that. We also added a privacy service. Karthik mentioned it earlier, Provide Privacy. We sort of look at this as a circuit registry and an L2. It also is similarly to Timber. And similarly to the commitment manager, I would say it stores a Merkle tree, sort of stores off-chain Merkle tree. But it does this in a way where the storage is actually sort of abstracted. So and we're also using NARC. So we sort of have this privacy service that allows you to interact with a very enterprise-friendly REST API, but underneath it's sort of abstracting it. It really abstracts away all of the, what proving scheme is being used, among other things, such as like what's the data structure? Is it a Merkle tree? Is it something else? In the future, perhaps other, it may make more sense to use something that's not a Merkle tree, but provide privacy will let you do that. And so, you see this, if you take this full picture and you look at it as sort of a full stack, like a full node or a full stack architecture for the baseline protocol. We recognize like the need for managed transactions, for organizations before they're really adopting and being comfortable holding crypto on their books. There needs to be a very easy way to pay for those transactions, pay for the transaction costs. So this sort of shows the consideration for how you can leverage the full stack within the context of managed transactions. And if you start to look at this from like an opportunity, an ecosystem perspective, and who will be operating these baseline stacks, you can start to peel away, and we'll show this in the live demos here in a bit. You can start to peel away some of the components. Like if you want to run the identity service microservice, or like the gateway, the blockchain, sort of the network gateway to the blockchain, or the privacy service, or the vault service, you could run those in somewhere else. They don't have to necessarily run on your local environment. Of course they can. And so what this sort of represents is how we have this hybrid architecture where you can sort of mix and match where you want to run your certain services. And it's going to be based on your tolerance, for security and privacy, as well as your sophistication in terms of SecOps, really, I would say. So this illustrates, how a managed, like a multi-tenant baseline stack can be operated outside of the context of each organization, like each participant in the protocol. This is exactly how we're doing things with Kona. Kona Run is the bottling harbor is it's an operated stack that Kona's operating, and each bottler, for example, has their own base participant stack. So if you sort of take a step back even further at a much higher level, the baseline per participant is really running a system of record integration proxy. So we mentioned earlier, like upserting a record will result in an outbound baseline protocol message. And so that this integration proxy is sort of the entry point, the gateway for messages that come in from, on the public internet from counterparties, the point-to-point messages, as well as the outbound message handling and dispatch for the baseline protocol messages that are originating in one or more systems of record that are baselined. Okay. So BRI1, like I said, we were in the right. It was just sort of good timing, which is why I think BRI1 has gained some steam in the baseline community. It's a commercial grade implementation. And I'm proud to say that it's really driving the API specification and standard. We got real world adoption with Kona, ServiceNow, and many other ecosystems, honestly, that are starting to take notice of baseline. So it's exciting, and we've done a lot of work with in partnerships with organizations like Unibright and Concircle, notably, to build highly automated integrations with, for example, SAP, and we're working on some other ones that are pretty automated as well. So being able to stand up a system of record or configure a system of record in the context of the SOR integration proxy, and then sort of letting that sort of work in the way with a multi-tenant SAP system, for example, and in the context of heavy enterprise middleware environments like MuleSoft and SAP PI, and really automating the ability to work in any of those conditions, I'd say is a pretty big highlight in learning. Another thing is L2, layer 2, there's so much noise in the enterprise space around L2s. And I think one of the things that we really want to focus on is how to reduce some of that noise and just make it just just like the privacy service abstracts some of the complexity there and brings for, sort of sets the stage to bring forth the best circuits that are needed for certain applications. I think we want to do the same sort of thing for L2s. We don't want to scare away enterprise adoption, because there's so much noise around L2s. Obviously, there's a lot of awesome innovation happening on L2. And we have many partners that like Connects that are leading that sort of path. Finally, optionality is very critical for enterprise adoption. You have to have the optionality. Customers have to be able to pick and choose what protocols they want to leverage, or sub protocols, if you will, in the context of baseline. What's interesting is a project called Base Ledger. We announced it with Unibright some months ago, and it really is looking to solve for creating some interoperability standards between layer 1 and layer 2. So that's a pretty exciting project that we'll have some more news on soon. But it's certainly really wanting to keep that in the context and focus really aligned with the baseline community and the standards work that's going on, because it just makes so much sense for for that layer 1, layer 2 interoperability to be handled in that way. So I think with that, I will hand it to Sam and let him talk about BRI2.
Yeah, thanks, Kyle. So yeah, baseline reference implementation 2 is kind of led by consensus, myself and others, but it is fully open source and available on the baseline GitHub repo. So we have gotten some community contributions, especially through, we ran a hackathon through Gitcoin and had some good contributions that came in that way. So I think BRI2 is a good way for people to hopefully get familiar with the baseline protocol and start tinkering around and eventually push some contributions back to the open source domain. Can you go to the next slide, Kyle? Yeah, so this is the architecture for BRI2. It's a lot of overlap with BRI1. And it's a microservice architecture. So each of these boxes here is kind of its own microservice. A lot of the components are the same as BRI1, or at least overall, we're trying to support the same standardized core API. So that the functionality is very similar to BRI1. I will just mention here that the dotted line or dotted box on the left is kind of showing the baseline server or baseline stack, as has been mentioned previously. And then on the right side is kind of our view of what a client would look like in this client server type of setup. So the client would be the existing software applications like an ERP system. So you can think of SAP or a ServiceNow, as Kyle mentioned, that Provide is working with. So some software application like that where you're wanting to pull some data out and ultimately deposit some sort of hash or commitment onto a public blockchain without exposing what that data is, but still getting the benefits of anchoring to a public blockchain. So you have that immutability, and you've deposited a record in a safe way on a tamper-proof ledger. So yeah, Kyle, if you don't mind going to the appendix, there's a slide focusing on how to send blockchain transactions. There you go. So how do you preserve your privacy when you're interacting with a public blockchain? So if I decide that I have some data that's important to me and I want to anchor it onto a public blockchain, how can I do that in a way where I'm not exposing who I am or exposing some kind of metadata about myself, such as the frequency at which I'm transacting, or certain timestamps about when I deposit hashes on chain might, if somebody has some data analytics running, could be able to kind of glean some information about my business activity. So this is kind of diving into the point where, assuming you've already run some setup where you have deployed a shield contract and a zero-knowledge verifier contract on chain. So you're at the point where you now want to deposit a hash into that shield contract, which is acting as your storage layer, but you want to do it in a way where it can't really be linked back to you. So Kyle mentioned provide payments earlier, which is kind of a managed transaction service, and this is showing Infura as the managed transaction service.
And we actually have a partnership with Infura as well, so Infura is involved in both cases.
Yeah. Okay. So yeah, I think it's a similar purpose and functionality here, but the way this can work and the way we have it currently working within Baseline is, if I'm the user in the upper left, I'm going to construct my transaction as I normally would, except I'm not going to sign it with my Ethereum address. But I am going to include the transaction inputs. In this case, I'm going to include the hash that I want to store on chain and a zero-knowledge proof that only I can generate. So the verifier contract on chain is going to be, in the simplest case, is just doing some signature verification. So if I deploy a verifier smart contract that is only checking for my signature under zero knowledge, it can act as an authorization layer where I'm the only one that can interact with the shield contract, because I'm the only one that can produce valid zero knowledge proof for that particular circuit. So if I send an unsigned transaction to Infura, the way their service works is they will accept that transaction, and as long as you have an Infura account and you've enabled that service, they're going to perform the signature on that particular transaction using their Ethereum address. So once the transaction reaches the shield contract on chain, the from address is going to be an Infura address. So to any sort of outsider, it'll look like Infura has initiated the transaction and sent it on chain. The key component here is Infura is not able to produce that zero knowledge proof on their own. So once the transaction hits the shield contract, it's first going to make a call out to the verifier and say, check this, basically check this authorization or authentication token and see, is it valid? If it is valid, it's going to execute the rest of that verify and push function and actually store your hash on chain. If not, it's going to revert the transaction. So in this case, my Ethereum address is not publicly visible to anyone, and anyone viewing this whole interaction cannot really trace this back to me. They just see an Infura address has sent a transaction to a shield contract, and all that happened was a hash was deposited on chain. So in addition to that, the advantage Kyle mentioned earlier is I don't have to manage ETH in my own account or have it on my books. I can let Infura, in this case, worry about paying for the gas in ETH, and I can recompensate Infura by paying them in a more traditional manner where I just signed up for a service and pay for that service. So yeah, I will just mention a lot of these. This has kind of been a development process over the last year or so, but a lot of these ideas were kind of generated from collaboration with E&Y and their R&D team. So a lot of the people we've seen today, kind of utilizing some of their work. So the shield contract name is kind of an homage to them and Nightfall, and then working with Kyle as well. He's done a great job pushing the protocol forward. So just wanted to give credit where it's due there.
Thanks, Sam.
Yeah, so that's it for this slide.
Cool. Sounds good. So I guess now we're going to do a live demo. Doing the show. Okay. All right. So what we're going to show today is the BRI1 sort of interface by way of a CLI that we've written at Provide. A lot of this stuff is well, the CLI is completely open source, and we've sort of figured out how to make the developer experience palpable. I mean, more like modern and sort of easy with the CLI. So essentially, what we want to do here, we've got this baseline command. So what I'm going to do here is list some work groups that we've created before. We've got one called MPC Sandbox, and we've got one called EY Summit Day 4. If we wanted to create a new one, like if you want to create a new work group, you can just do provide baseline work groups in it. And then you get, some prompting, so we can and then it basically says, hey, pick a mainnet, which is cool. You can select any network. Bitcoin, don't pick Bitcoin for this, but then it says, what organization, do you want to use? There's also an organization's init command that you would run to get an organization. I'm just going to use mine called KT. And then the way this works, like BRI1 does in the baseline repo, by deploying the org registry contract, which is really like the global contract, and you wouldn't be deployed. That was quick. Wouldn't be deployed that often, or ever, maybe just once on mainnet, but we deploy it just for test purposes. And so you see here we've got this initialized baseline work group, and I could say baseline work groups list again. So I've got now my EY Summit work group. So if I wanted to invite, for example, someone, provide baseline work groups, participants, I believe, invite. Okay. So SS Inc., right, for Sam. Let's see. I'm not going to use Sam's real email. Sam SS Inc. That's not a real email at Mesh, so we'll use it. Okay. And so what happens is, oh yeah, then you got to select the work group that you want to actually invite Sam to, and the organization that you want to use again, and that this will be we'll make that a little better. So we've gotten this VC that we can give to Sam, and it's just basically this. So you see, like, a couple of basic facts about about the invitation, and we're giving some bare authorization here for Nats. And so now what I'm saying is, when I give Sam this token, Sam can, and I could give it to him out of band, remember? So the email, I could Slack it to him, whatever. I'm giving Sam permission to write messages into my baseline environment. That's what this is. That's what this does. And then the first thing that will happen once he connects, there's actually an EC recover. So I mentioned earlier an Ethereum address that each organization is associated with, and that address is used to authorize. You can make subsequent requests for issuance of a VC in this manner. By basically signing a message and sending it off chain to each counterparty in the work group, and then they're able to verify. They basically do an EC recover on the signature on the message, and if it matches the address, then they know, okay, they basically can look you up on chain, and that's that's how the counterparties are sort of resolved. So if I were to do like provide baseline, let's do a list here. What you'll see here, if I list the participants, is that we have my organization, and we have a pending invite for Sam. So if I were to do the same thing, for Karthik, we would have, another invitation for Karthik. So what we're going to do is we're going to use, whoops. Baseline. So what we're going to do is we're going to use this EY Summit Day 4 simply so we don't have to rummage around for out-of-band tokens during the demo. But so what we've done is we've basically run that previous step that I just showed that generates that VC, the invite, and I've delivered those out of band prior to the demo today. And so what we're going to do is, so I guess we've got can you guys see this? So what we've got here is a Teams window with Sam and Karthik on it, so that we can share sort of their perspective of the demo. So we'll see how this goes. So Sam is going to go ahead and accept the invitation for Sam Supplies, his organization, and then Karthik will do the same thing. So that's done. So Sam's been, so if I look at the participants in this work group, the day 4 work group, I see that Sam has been, and there's Karthik's invite as well. So Karthik, do you want to share your screen and accept your invite too? This is an experiment in multi-screen. So Sam's going ahead and running the baseline stack. Sam's on fire over here. What he's doing right now is saying, yes, he's going to essentially expose a tunnel for the API and the messaging endpoints to expose his baseline stack to the internet so that we can send messages. And so you see it pulls the containers it needs from Docker Hub. Another interesting thing is,
just to be clear, I wanted to mention that the exposing the tunnel is just intended for development use. It's not a production.
Exactly. Yeah. In prod, you wouldn't tunnel out. You have obviously statically configured ingress and egress. Thanks for mentioning that, Sam. Okay. So so I guess sort of to tie things back with stack run. So I haven't run the stack yet. I need to run it still. But if you look at all the options, the optional flags for the run command, you'll see that there's some that are like with local ident, with local in-chain. So essentially it lets you mix and match which parts of the stack you want to run locally and which parts of the stack you want to run on someone's with some operator. So for example, Kona Bottlers, the ident, their ident service is not provides hosted environment, but rather the Kona bottling harbor. So that's one example. Karthik, were you able to join?
Yep, I just sent a join request. Just waiting for it to get resolved.
Okay, cool. So Sam, you're running your stack. I'll go ahead and run mine as well. So let's provide baseline stack run. And again, which work group are we going to use? What org we're going to use? So this is just like asking me if I want to authorize a token for the org so that the service can run. And then this sort of says, hey, what's your primary system of record? We're going to use ephemeral in memory. I'm going to need a tunnel, and there we go. And so then my stack will start, and then see my tunnels are established, and let's see if Karthik got in ever. Karthik, you never got in? Do you need a new invite or something? Oh wait, you're muted.
I might need a new invite. Looks like the token is not associated with the current work group.
Oh, okay. Let me give you a new one. Maybe I may have created it against the wrong one. Here, I'll stop sharing and send it to you. 1 second.
But I think we have like only 2 minutes. If you would like, we can continue on with the baseline message sending piece.
Okay. Yeah. Cool. No worries. Okay. But yeah, sorry, I probably sent it to the wrong place. All right. So Sam, so Sam and I are running the stack, and if you see these containers. This is sort of the appliance, the set of containers that represents the smallest footprint for the baseline stack. And then, so I guess what we'll do is so Sam, you want to share your screen still, and tail the NATS log, tail the NAT server log.
I think I lost my sharing capabilities. Sorry, I'm not too familiar with Microsoft Teams, but if you just tell me when, I can send the message and see if it shows up on your side.
Yeah, that'll work. Okay, hold on. Let's do it this way. I'll send a message first, so you can sort of see what the UI looks like, and then you can do the same, and I'll share my screen. So you just pick the message type, and again, this is just for development purposes, so you can get started sending baseline messages with your counterparties very quickly. So like this would just be like a hello world object that's going into. So then we send that, and then Sam will be receiving messages. All right, Sam, let's do it the other direction. So we got a baseline record. What I'll do now is I'm gonna tail the NATS log. So there you go. All right. So go ahead, Sam. Send me a message of your own there.
Okay, it just got sent. So what's going on behind the scenes here?
Send it one more time. I cleared the logs.
Oh, okay.
Yeah, also at time. I think we should wrap up.
Yeah, this is we're almost through. I think this is worth showing, and then we can move on. So Sam's sending me a message. What you're gonna see is the R1CS binary gets synced basically. It's like so Sam just kicked off a new baseline workflow because he didn't specify a baseline ID. It got generated for his baseline stack, generated the baseline ID, and then synced the circuit, the R1CS binary with me. So you saw it was a general consistency circuit. And then what we see from Sam is another message here that has here's another message right here that has the proof that was generated by Provide Privacy. So we have a valid baseline state transition right here. I'll cut it short there, just in the interest of time. Sorry for running over, if any. But yeah, so I'm going to go back to whoops. Sorry. All right. All right. So live demos. Really the standard, the OASIS standard, just to move forward. How are we looking on time?
I think we're out of time, Kyle.
Yeah, I think we may be. So we want to really drive the OASIS standard. That's happening. I think by the end of June, we want to have the first draft ready for review, and it's been going quite well. There is a link to Swagger Hub, where you can actually go and check out the API standard that we've been working on. And I would encourage everyone to do that and get involved with baseline, because it's definitely going up and to the right. Sam, you want to say a few words on this?
I think we're kind of out of time here. So
okay.
Yeah, I'll just say thanks for having us on here. And if anybody wants to get involved or learn more about Baseline, you can reach us through the GitHub repo or via the Baseline Slack.
Yep. But yeah, thanks a lot for having us. Sorry for being a little bit long.
Thanks, everyone.
All right, up next, we got some more block talk with Arwin and John. Mike is yours, gents.
Hey, John.
Hey, Arwin. What'd you think of that last segment?
It was heavy. I'm being on this journey with you from the beginning. It's amazing to see how far the community has come, and really about a year, right? So it's laying a lot of great foundation, I think, for enterprises to really consider taking advantage of the mainnet, right? Getting enhanced data integrity without the leakage that comes in the way of doing it traditionally.
Yeah, I think my advanced age is now preparing me for the humiliating or the humbling experience of at one point knowing or thinking I knew what was going on, and now it's so advanced. It's getting so advanced that I'm struggling to keep up with the with the detail to the point where like I have to really work to be able to say, yeah, this is exactly how this thing works, and this is exactly how this thing works. It's just moving so fast. We have so many smart people on the baseline protocol now. I mean, it was just a few of us, 2 years ago, and what's really cool is, I should say, is we're starting to see new people pop in. I mean, like Kyle he's building a business. I'm building a business. EY is building crazy stuff. All the original, York Rhodes is doing actual supply chain work at Microsoft. And so we're kind of busy now. And luckily, and this is a sign of health of the community, there's all these newcomers coming in and taking over and, asserting themselves. And I really, people like Anais Frank and Dhruv and others.
Yeah, and that's something that I got from even the presentation, right? Like Infura's offering component provides offering component. We really want an ecosystem of providers to support this, right? Because this is also foundational technology that needs to be there to fully take advantage of the blockchain too. And this is a blockchain summit, right? The point that Kyle made around tokenizing output, right? Where does the baseline protocol meet the other values and benefits of a blockchain? The fact that we can capture value, right? And we don't double spend that is still an important component. But we have a lot of other stuff that enterprises need to do before they get to that place where they're ready to exchange value. So real examples around invoicing, right? Like there's a lot of be a step in your journey, right? And then when you get to that, right, the output of that is something that you do want to put on chain, right, in a tokenized way, and be able to exchange that. So I do think it's a very critical piece. I know we're already running up on time. Anything else you want to deliver? Also as a chair of the community for Baseline, that you want people to walk away from here.
Yeah, I'll say one PSA real quick. There's $100,000. I said $100,000 that the Ethereum Foundation has given to the Baseline Protocol community as incentives for R&D and enablement work. So if you would like to make some money doing good service to the open source public domain community, you can go to baseline-protocol.org. And you'll see the link right on top to submit your grant proposal or your bounty proposal. You could say, well, I don't want to do it, but I really think this should be done. And then we can make it a bounty on, say, Gitcoin. And we're very grateful to the Ethereum Foundation. In fact, I think that's, they're going to start a trend for doing this. It's really exciting. So come on in. There's already there's a Zero Knowledge Circuit grant already out there. There's somebody's building Hello World for Baseline, making it really cool. So there's a lot of very interesting things. So and I'll also say, Arwen, I'm sure that we've been discussing this. There's a real opportunity here. The most obvious thing is you can say baselining is great. I need to be sure that my record is your record without putting that on some big shared threat surface like a blockchain where everybody can see it. Companies tend not to like that idea. Fair, right? But what really is a powerful thing is if I get in an elevator with a CEO and I say, look, I'll buy your invoices the minute you have delivered your goods, not 90 days later, if your invoice is baselined with your customer. And I'll buy it for a ridiculously low rate so that you want to do all your invoices that way. That's a conversation that's going to get me all the way to the top of the elevator. So those kinds of use case stories are what's going to really drive the community forward. I think at this point is to say, yep, baselining is a good technical kit and it's a good design pattern. But the punchline of the joke is something, and that's where tokens and baselining come together, right? You're going to have DeFi tokens that are secured by baseline database records.
Yep. I couldn't have said it better. Thank you, John. I do want to try to get us back on track. So up next, I'm excited to say please stay tuned in. We have an awesome talk on considerations for production. Obviously, we know the blockchain market has continued to mature. The world of building lots of prototypes and proof of concepts has kind of come and gone, where everyone's eyes on how do we make this work for real in production. So with that, we unfortunately don't have Sam Davies lined up. We have Yaniv Sofer stepping in to take us through with Sirkin as well. So I'll turn it back to you guys. Thank you.
Yaniv, Sirkin, the mic is yours.
Thank you. All right. Hi, everyone. Thank you, Arwen, for the introduction. My name is Yaniv Sofer. Can you hear me okay?
Nice and clear, yes.
Perfect. And Sirkin, are you with me as well?
Yes, I am. Can you hear me?
Yes, fantastic. So I'll start by sharing my screen here. Let me know that you can see. Oops, advancing a little bit quickly. Can you see my mouse here as well? I'll be clicking through some stuff. Okay. So the presentation should be up for everyone. And so Sirkin, if you'd like to start, just introducing the session, and we can go ahead after introductions. I'll take over.
Yeah, sure. Hello, everyone who is watching and listening to us. My name is Serkan Ersanli, and I'm working for EY as Off-Chain Traceability Technical Lead. So today's last session of the summit is around considerations when taking an enterprise blockchain solution to production. And since Sam is sick today, Yaniv is presenting the initial part of the demo. So it's over to you, Yaniv.
Sure. So just a brief agenda. I'll be talking about some of the technical, platform considerations and also the governance considerations, right? Just high level, what sorts of architectures. Sirkin will jump into the very specific technical considerations and some of the use cases that we have ready to go for you. So as Sirkin mentioned, he's the off-chain traceability tech lead. I am a technical lead and a manager here at EY in the US blockchain. I've been working primarily with our financial services clients over the past, 2 years now, taking production blockchain systems, taking blockchain systems to production. And so I'll just jump into our first topic here. How do you take a platform to production? There's a lot of what we need to do, starting with an idea, right, all the way to having creating business value in a production system. And it's a little bit daunting when you start to unpack it. And we want to look at it from two lenses. One is the technology side of things. And in some ways, the technology side of things may be a little bit more straightforward, a little bit clearer in terms of engineering tasks, which we'll go into a little bit later. The second piece is really around the fact that blockchain is an ecosystem play, right? You need multiple participants, and in fact, this is the first thing that we ask when we talk to our clients, and when we think about designing blockchain solutions is, how do you have a lot of participants involved in the system having all of their needs met, both from a technical perspective, but also from a governance perspective in terms of security, and gracefully onboarding and offboarding them. And so in that regard, the non-technical piece of how do you get people on board, how do you reach critical mass, so the network effect is in play, is a little bit more open-ended. And we have some considerations to go over today as to how we do that. So I'll start by talking about the development flow overall for blockchain systems. It's not fundamentally different from the ideation step when you have an idea, maybe start to whiteboard, get some designs in play. Once you know what direction you want to head in, you need to get that first built prototype in place. And there's 3 different types of prototype approaches in this next box, the light bulb here. And we've broken it out to proof of concept, proof of value, and minimum viable product. Proof of concept, you could think of it as a focus on feasibility. So can the technology do what we would like it to do from our ideation phase? And in some ways, this was a lot of what we did early on, working with our clients and internally to prove that the technology actually is feasible. But we're starting to move away from that more towards proof of value and minimum viable product, where proof of value, we're actually ensuring that we can meet some more of the business needs, that there's actually an ROI coming out of the system that's being built. And lastly, to distinguish minimum viable product from proof of value, the MVP is focused on actual system designs and integrations, and really understanding what this product, this architecture needs to be in order to work in a production-like environment, or as close to it as you can get. From there, we move on. We start to actually integrate, small-scale testing and actually interact with potentially real data at this point instead of mock data, and start to get some value. And lastly, going to production. When you have a full-scale system that's highly available, meeting SLAs, and doing what you need in production to capitalize on that ROI that we proved here in this ideation, in the proof of concept or the prototype phase. What I do want to highlight on the pilot and the production phases is there's a key difference in some of the technology and governance approaches. You want to get as close to the full technology implementation and governance implementation that you see in production in this pilot phase, but some of that can take a long time. As you'll see, I'll highlight why it takes a long time, and so it may not be ready quite yet at the pilot phase. So a lot of times it'll evolve the governance and the implementation to really meet the production needs. So let's unpack the technology portion of it. So from an architecture perspective, a lot of it is not new, right? So there's a lot on this slide. So if you can follow my mouse, right, there's 2 ways to enter the system, either from a GUI user interface, or from an enterprise or legacy system making a call, and you're coming into a management gateway system. The call is being made, again, either initiated by a user or one of our systems, and we go through the traditional identity and access management portion, the controls that already exist within the enterprise. But for blockchain systems, we add 2 key additional elements here. This is where custody can take place, right? The wallet and the key storage portion of it. And so it's where we have some additional security concerns, and we keep it coupled with the identity and access management portion. So the call comes in, it gets authenticated. Maybe we need to get some additional enterprise data, right? So this is where you may make external calls, again, linked to the underlying systems. Say, you need to get inputs for your token, or you need to see that there's been an agreement signed, a legal document before you tokenize some sort of contract on chain, or put it in a smart contract rather. So this is where this integration will happen. Just again, these are incoming calls. These are outgoing calls to retrieve information from potentially enterprise data systems. And lastly, we get to this blockchain services component, right? This is where we want to highlight. So a lot of the differences are starting with Ethereum. In this case, this would be where the nodes run, the dApps in terms of smart contracts and the actual tokens and the token standards that we have. So, there's no need to reinvent the wheel when it comes to blockchain systems. We want to leverage existing design patterns and actually layer on the blockchain, which also helps when we're conveying to potential adopters of this solution. You don't have to rethink all of your systems, right? You're adding incrementally adding components to what you have. and applying it to a blockchain. So while this is all, this design is all well and good, as we mentioned, the real value of blockchain comes from the network ecosystem play here. And this is where we start to add complexity. So if I move on to the next slide, right, it's a network, it's an ecosystem, and there's some additional considerations that we have. And what we're highlighting here, if all of these, you know, smaller components are really the previous slide that we've identified. And what I want to highlight is that this shared blockchain layer, right? This is where the distributed part of DLT blockchains comes into play. And this is where the ecosystem derives value, the single source of truth, the single set of processes and computational environments where calculations may take place. The same functionality, right, that exists for all of these participants, and we're able to standardize it across. So some of the key questions that we need to look at are, you know, each of these systems, let's say, is a different business. They each have different requirements for this blockchain component, these tokens, these smart contracts, and how they will run. In fact, some of your participants may not even be ready to run their own nodes, but they want the value of a blockchain. So again, understanding some of the requirements that are coming from them and how to address it is absolutely critical in designing this blockchain component. Or we're not yet at a place where DAOs will replace existing businesses, but who knows? Maybe it'll come sooner than we think. But for now, you know, when we think about our vision here at EY, that blockchains will do for business ecosystems what ERP did for the single company, this is where the blockchain excels as this cross-enterprise ERP-like system, bringing in a single source of truth, interconnecting disparate organizations and disparate systems, acting as that layer, that interconnecting layer. And agreeing on how to work together is absolutely a challenge. So how do you get these systems to integrate to even agree on a solution and an approach? And so there are two types of approaches on how to build an ecosystem. And the first approach is actually the second bullet here, but I'd like to start with that one, is building the platform first. So you can think of it, sometimes you can think of it as a quote unquote bully approach, right? Where there's a large enterprise that controls a very big part of the market. An example of that could be maybe Walmart, right? If they're creating a blockchain and telling all of their suppliers, you have to get on my platform in order to continue doing business with me. And they know that they can apply pressure to smaller businesses that depend on the large enterprise volume for their business operations, for their success. They can apply that pressure and build a platform first and impose that platform on their ecosystem participants. In that regard, it's quicker to do, right? Because you're focusing it onto single enterprises consideration or a single set of requirements coming from a consolidated set of decision makers, but it also focuses the risk and the cost, because what if your participants don't want to do it? What if another ecosystem comes into play to replace you, right? There's some fundamental challenges associated with that. The second approach, when we talk about building an ecosystem first, in market, you can think of it like some of the consortiums that were built. While the advantages of sharing the risk and the costs of working in a consortium sound great, in practice, there's also the added overhead of governance or decision-making by committee. And so every decision that you need to make, depending on how you structure the consortium, assuming equal participants, there's maybe voting, there's a lot more voices in the room, and inherently it's a longer process with a lot more challenges, but hopefully in the best case, there's a lot of buy-in from a lot of different enterprises, the consortium members expressing their needs, and you now have an ecosystem that's potentially meeting all of their needs. But again, the time to market thing is crucial, and we're talking significant extended time periods here. And what I want to add as well to consider is also any additional changes that need to happen after the fact, right? So any amendments to the original design or the original technical architecture, or even the rules, become an increased burden with all of these participants. So you have your participant, let's say you've built your ecosystem. Now we need to get different parties actually on it. And what's really cool with the blockchain is that how you connect to the blockchain is entirely abstracted, right? Somebody can run their own node and just interact directly with a smart contract, right? When you think of dApps, right, it's a front-end browser client sending calls to a blockchain, getting data, using that as its backend system. That's sort of the purest form. You can, this direct connection, you can develop your own system to integrate directly, where you may build sort of middleware, communication, API gateway, right? Everything that we've outlined and designed. You can work with blockchain.ui.com, right? That's the tools and the suites that we're building to really help you increase that adoption. And one thing I want to highlight that I've seen a design pattern that has been incredibly valuable when we're working with our clients has been to allow what we call sort of a spectrum of integration, where in some of these consortium approaches, or even private networks where there's a network operator, you want to reduce the barrier of entry, right, in terms of technology. You want to meet your potential ecosystem partners where their technology capabilities are. And really, you want to give them as much of the incentive and the benefits that you can get from the blockchain while reducing the risk and the implementation costs. So when we say a spectrum of integration, you could think of it like, I'll actually hop back to these slides a little bit here, where you may offer a completely packaged solution here, where you give a UI to a potential participant who's not technologically sophisticated, but is an important part of your ecosystem. You may allow direct API access, but still, so they can build a custom UI or directly connect their systems, but they don't want to deal with, you know, the key and the wallet management pieces of it. You may ultimately run the nodes on their behalf, if that's something that's a requirement, or for the most technically savvy, or even those that are ready, they can run the entire set, these microservices, these components as a whole. And so really, there's a lot of value in allowing different integration options and taking this modular approach. And we found it incredibly helpful in facilitating adoption and reaching critical mass by reducing barriers and incentivizing adoption and meeting folks where they can integrate, given their current technology capabilities. So the next part is stepping away from the technology, as I mentioned at the beginning, was the governance considerations. And there's a lot going into the governance, and I'll try to highlight some of the key elements here. As you'll see on the next couple slides, there's a lot on here, so I'll try to focus on just a few of these and mention specific considerations that we've seen are critical or higher value here. So starting from the bottom, right, the infrastructure and governance considerations of the stack. Starting with making a decision on what network you want, right? What protocol, how you're going to deploy those nodes, monitor them, and specifically on the support and maintenance. Say there's a protocol level update, how do you roll that out? What is the expectation of the participants who are running their own infrastructure? On what timescale are they expected to update, especially if there's a non-backwards compatible change in the protocol and some of the things that are coming into the changes that are coming in, as well as backup and disaster recovery. So this infrastructure governance step is focused on making sure that the participants in your ecosystems, those that participate in the blockchain, are meeting the technical needs, the infrastructure needs, to be high quality participants, right? They're highly available, able to keep up with throughputs, right? They're able to handle disasters and recover. They're able to identify through monitoring very quickly any anomalies and any challenges happening with their infrastructure. And again, if you think of it from a infrastructure layer, how do you ensure that they're a good participant? And what are the rules that you set forth and requirements to require of these participants to be participating with you? And on public blockchains, this becomes a lot less of a concern, right? A lot of these decisions are made for you in terms of the network, the upgrades, and but still the deployment and being available to transact is crucial. From a network governance perspective, when it comes to private networks and also in public networks, comes the on and offboarding, right? So how do you get and discover additional partners? And what happens if somebody needs to be gracefully exited for any number of reasons, right? They're not meeting the requirements, you need to sort of block them. What are your repercussions there? As well as just general operations and requirements there. At the application governance layer, right, it's the ability for some of these off-chain integration, getting relevant system data and any off-chain data that you store, again, being readily available and thinking of it from the context of how do you ensure that the systems are in place, moving away from the infrastructure and the network governance layer to the actual application stack and the API services, things like high availability, data coming in, potentially attestation, ensuring that what's going into the blockchain is accurately reflecting what's happening in the real world. And so the last piece I'll leave you on the governance here is specific to the consortium approach, and where you have a board of directors that are overseeing these decisions that coming into here. Right, starting with the legal entity, which is important if there's any challenges coming up. Looking at some of the software elements in the support, choosing service providers. Say if you want to use a company like Provide to run the nodes, right? You want to provide that infrastructure and those elements over to the participants to allow them to meet the needs. Specifically looking at technical standards is huge, choosing which standards to use. And what I want to say is, at least in the consortium approach, I've found the identity piece being crucial, because as a consortium, you're acting as a gatekeeper, deciding who gets to participate in your consortium and who doesn't. And the next piece is dispute resolution. The governance approach of Murphy's Law, anything that can go wrong will go wrong, anticipating that and having a clear process in place of how you will resolve dispute that everybody has agreed to before a dispute even arises. And there's a lot of work that goes into the identity and access piece, onboarding and offboarding, as well as the dispute resolution portions of it. And that's, again, beyond all of the application development, secure software development, lifecycle considerations, security, high quality code, the legal and the regulatory perspective, et cetera. So with that, I'll hand it off to my colleague here, Serkan, to jump in and dive a little bit deeper into the technical considerations.
Thank you, Yannick. Greetings again, everyone. I hope you can hear me.
Yes.
Awesome. So through a couple of slides today, I would like to do an overview of principles that we have been continuously applying for blockchain.ui.com, software as a service platform, and then share a high-level definition of how we integrated Bureau Peroni use case into EY upstream traceability solution. So going back in the time, when we started building blockchain.ui.com platform with my colleagues, so we had first prioritized and focused on principles that would lead us to design a best-in-class enterprise SaaS solution. Basically, the platform had to be flexible and dynamic to allow us easily to implement and publish new features in line with EY's and our clients' requirements as soon as possible. We also had to ensure that new functions shouldn't break the existing functionalities when they moved into production environment. So each new implementation had to be well tested prior going live in terms of unit testing, integration testing, security testing, and so on. So in brief, the applied processes and architectural design had to help us to bring new features to life incrementally into our production environment, provide a very fast time to market, and ensure all features are continuously well tested on top of a flexible infrastructure. In that regard, as EY Blockchain Global Innovation Team's approach has been strictly apply agile methodology and create and apply end-to-end seamless CI/CD process design, as well as following up well-architected principles for the architecture design, as I'm going to talk about later. So I will go over each principle through next slides. As part of the DevOps philosophy, the software lifecycle of blockchain.ui.com consisting of development phase, then testing phase, deployment phase, and the operations phase. In terms of the tech stack, we create tickets for each task on Jira tool. We develop on Visual Code with our mainly used development languages like React.js, Node.js, and GraphQL, and also as well as Cypress and Jest for testing. Containerization is one of our standards amongst all EY Global Blockchain development teams. And all our pieces are running on their own Docker containers as microservices. Our code base is on GitHub, and we also use GitHub Action workflows for CI/CD processes to deploy regarding container images per environment onto Kubernetes pods that are located on Microsoft Azure Cloud. We also developed an in-house Slack bot, which we call it as Optimus Prime, for developments of the latest code to production environment through Slack channel. So it also helps for the whole teams to follow up developments on Slack, so it provides a great visibility. I will talk about further this end-to-end process. So there is a short summary of the bottom right of the screen. But first, I would like to mention how we handle new features with agile methodology for blockchain.ui.com. As we get requirements from EY clients and according to our product roadmap discussions, once a new feature request comes in, we first assess it deeply within agile ceremonies and evaluate it in terms of benefits to our clients, then put the new feature into our product roadmap and prioritize accordingly. Then we create new tasks on related product teams Jira board. So the deployment team starts implementing it by picking up those story tickets from the Jira board. In case the new feature requires an analysis, we start with research tickets first, and then create architectural design accordingly, start the architectural discussions, and then in the end continue with the development tasks. So within the next slide, on top of the brief explanation on DevOps that I mentioned in previous slide. We expanded and enhanced our processes into DevSecOps. So the DevSecOps is a combination of DevOps plus the security workloads. And we have injected further security testing into existing workflows. So static and dynamic code analysis are performed within the same CI/CD processes seamlessly. If you dig into the details of our end-to-end DevSecOps processes here, it starts with immediately after a developer creates a pull request into own branch on GitHub repository. So at that time, development workflow is triggered by GitHub Actions, that is to validate the pushed code in terms of linting, unit testing, integration testing, and security testing. Then the workflow continues by building related Docker container and pushes the image into Docker registry by labeling it with its specific PR number on GitHub. So another GitHub action follows that, and it deploys the specific image through manifest files onto a Kubernetes pod that locates in our development environment's Azure virtual machine. The same workflow, by the way, is also triggered, and this cycle is reworking again whenever developer pushes a new commit onto existing branch. I think one of the best features we implemented here was to publish each PR over a specific URL that you can see here. So in that regard, anytime a PR is created, that specific version of code can be reviewed over a specific URL in product name .pr-pr number.devblockchainey.com format. So when a PR is under review, as one of the reviewing standards, we force at least 2 reviewers to approve the PR before merging it into master branch. It is by default disabled on our repositories by GitHub admins. And it is also not possible to merge a code into master unless the development workflow here is completed successfully. So after all, once the code reviews and workflow testing are passed, then we allow the PR to be merged into master. So that triggers the next workflow called release workflow, and that is only executed when a PR is merged. It reviews the merged code again. It revalidates it, including running the whole test from scratch, and then repeat the same cycle that is done for the development workflow here. However, there are some differences at that time. So release workflow, apologies. So the release workflow builds and creates the Docker image with latest label to keep the latest version refreshed on the stage environment. So it deploys on the stage environment and it refreshes the deployment on stage.blockchainey.com. So after a PR is merged, there remains and latest image on stage environment exists. So we keep the latest version of our image on the stage environment. And release workflow deletes the old image and the deployment on the development environments Kubernetes for better resource management. And in the release workflow, we cut the release through semantic versioning, and developers are forced to commit any code into any branch in case the commit statement is convenient for conventional commit standards, because the semantic versioning logic applies the versioning algorithm according to the commits that are made over the PRs. So it is providing as an output the XYZ format, the major, minor, and the anti-fixed versions. For instance, every commit starts with feed prefix if the PR is related to a new feature on blockchain.com. So that is also secured by us with further linting controls in our repositories, and the commit directly fails on developer's local setup if it is not well formatted according to semantic versioning. And after all, in case the latest version of blockchain.com code is approved by product owners and tech leads, then we use Optimus Prime, the Slack bot, to deploy desired version into blockchain.com production environment. And in the next slide, I'm going to talk about the Azure well-architected framework, but it also applies on the AWS platform. So whilst building blockchain.com platform, we adopted Azure well-architected framework and followed its related set of pillars to build a dynamic, flexible, reliable, secure, high-performing, load-balanced, and high available SaaS platform to our clients, by also backing it up with a geographically duplicated disaster recovery environment. A well-architected framework here can be considered as a framework that helps architects over architectural best practices and across those set of pillars to design and operate a reliable, efficient, secure, and also cost-effective architecture on cloud environment. It provides a set of questions, and as architects, we are able to review an existing or proposed architecture on cloud by this framework. So by the help of that approach, amongst the whole blockchain.com product teams, we are easily discussing on architectural discussions and new implementations that need some changes on existing infrastructure and architecture through multiple alternative solutions. In line with the designed infrastructure here, so you can follow, the customer journey starts with blockchain.com web and API users. Users log into the system. So both access points are managed by certificates over HTTPS, and the authentication is confirmed over Auth0 integration. So then blockchain.com clients are able to navigate over UI, or the integrators call secured API endpoints over provided client ID and client secret credentials that is provided by UI. So the request first reaches to Azure Application Gateway and routed to the pods of requested product through ingress controller. Each application locates in their own specific Azure Kubernetes services instances on related virtual machines. So in terms of the blockchain integrations, we provide connections either Ethereum testnet or mainnet through simple clicks on network selection interfaces over UI. or the parameter passed through API endpoints. The blockchain transactions are going over the Ethereum network through infra integrations and EY tailored smart contracts that are tested with EY's testing studio tool as well.
So maybe being mindful of time here.
Uh-huh.
I think we're coming up on time. I don't know if we have somebody
Yeah.
monitoring us, but maybe let's go into the case study. It's one of my favorites.
Yeah, awesome. So we are really proud to implement our first enterprise customer Birra Pereno on blockchain.com platform. And I think as you have listened the Birra Pereno use case in details from functional and business perspective within this summit, I would like to go over a high-level architecture of it here and how we implemented it on blockchain.com. So as UI is developed separately, from blockchain.com perspective, the major task was to provide the API endpoints for an end-to-end tokenization service of malts, grains, and beers that are to be tokenized over ERC-721 non-fungible tokens on Ethereum mainnet. And the architecture here is, as you can see, the malts, grains, and beers data are collected from partners over SFTP. And then through a landing page developed on UI, the representing tokens are created for each batch of beers on Ethereum network to allow Birra Peroni users, Birra Peroni customers, to confirm the batches for the bottle of beers they are holding over immutable Ethereum network. So the main Birra Peroni integration has been over our API endpoints. So it is all from me. It's over to you, Yannick.
Great, thank you. So I just want to wrap up with key takeaways, right? So this question is sort of the crux. 80% of blockchain platforms are predicted to not make it past the pilot stage, and you can, we've referenced the Gartner study. How do we make sure that ours do? And it really starts from early on in the design or the ideation phase, asking the right questions and qualifying solutions. We have 5-point tests that I'm sure was covered elsewhere, but really starting with understanding if there are multiple participants in the network to ensure that there's ecosystem value coming in, that there's a network foundation to the blockchain solution. From there, when we talk about the prototype phase, we really focus on building high impact, minimum viable products. And as you remember, I mentioned we're moving away from proofs of concepts where you're just highlighting feasibility, because the feasibility for an Ethereum, a blockchain like Ethereum, has been tested time and time again, and you can confirm feasibility elsewhere. Really, we want to build the MVP to get to a point where delivering value early and often, right? You're delivering value and expanding that value, but from day one, you should be getting some sort of benefit from this. From there, there's a network play, as we discussed on the technology perspective. We want to incentivize and also incentivize participation and also reduce friction to participate. So to that end, we talked about how we keep the tech stack consistent with existing design patterns, so there's no overhaul to your technology. You're just extending what you're currently doing. We're using standards wherever possible, and in fact, open source standards at that. So we'll extend even further, something that anyone can access and read. It's not, there's no, you don't have to pay or to be able to adopt these standards, and therefore you can build your solutions to quickly interoperate. Next, we talked about the spectrum of integration component, and that's really going from potentially all the way a white label, entirely hosted solution from a service provider down to a self-hosted component, say, running the entire stack for a given participant. And as you saw from Vera Peroni, right, they wanted to integrate their systems directly. They didn't necessarily want the UI coming from a third-party provider, but we provided some of the core blockchain elements of smart contracts and connecting to the Ethereum network. And then lastly, we talked a little bit about the governance, and really like any good relationship, right? Interpersonal or business or otherwise, governance really boils down to having really clear expectations of one another. And the biggest success we've seen on the governance front is to ensure high quality participation. You want to very clearly articulate the benefits that you will get, but also the obligations that you'll have at the various levels. And all of these components, there's a lot to consider, but all of these components come together to really help us create high quality pilots that are really really likely to get to production. And we emphasize, right, even from the design phase, that everything we're building is with the end goal of production in mind. We want to see the light at the end of the tunnel and constantly work towards that to ensure that we're focused on building scalable, quality, secure, extendable, and we're meeting the requirements of the entire ecosystem. And so with that, I think that's all our time. So I'll hand it back to our hosts.
Thank you
very much.
Yaniv, Serkan, thank you. Yaniv, Serkan, thank you. So you both very much. Wasim, thank you very much. This brings us to the end of our summit. And for those of you wondering, what this means here, the shirt with a collar, is that I am all out of new t-shirts that you haven't seen. So if you have tuned in for the entire summit, you have now seen the complete and total current t-shirt selection. A few closing comments. First of all, I want to express my immense gratitude to our production crew in EY in Toronto, led by Wasim, to our marketing team, Marikit and Lindsey, who have monitored and led and reviewed every single minute of the last 4 days in exhaustive detail, and to the folks over at the Ethereum Finance Forum on Reddit, who have been incredible partners, advisors, thought provokers, and question answerers, not just during the summit, but really for the last couple of years, because they've just been incredible. So that's all been excellent. And we've had one after another of amazing guests. From all 4 days of our summit, every video is chapterized and on the EY blockchain website. And if you go to the place where you registered, which is the summit site, you'll see those. You'll see the replay days by day. You'll see all the presentations, and all of today's presentations will be chapterized and summarized with the presentations that we have on the site as well. And that'll probably be done in sometime in the next 12 hours or so. You have just a few minutes left to collect your proof of attendance protocol token. So please go and do that. There's the URL that is visible. If you want to go and check the other content, we'll have a link up at blockchain.ey.com in a couple of days if you can't remember the original publication site. And I think that's really it. I'm just incredibly grateful for all the participation, incredibly grateful for all the support that we've had. I love having these weeks because it forces us to organize, structure, manage, and take everything that we do on a 2-week sprint basis and summarize it and go back up one level and talk to other people about it who don't have all the assumptions that we do and are going to ask great questions. And so that's been immensely helpful. And it's really great just to have this event once a year where we engage the rest of the world. We'll never be going back to only in-person events. We will have one in person in September. It will be broadcast as well. This time next year, we'll go back to having our annual EY Blockchain Summit and Blockchain Week, but we'll never change in the sense that we'll always continue to have these be broadcast and available to the broader community, because even the least well-attended session in the last 4 days had more people than the best attended session when we did these in person. And the level of engagement was just as high, sometimes much higher. So with that, we have some very nice closing credits. I want to say thank you again. Thank you for watching. And I wish you all a terrific weekend. Bye-bye, everybody.